Learn how to problem solve with JavaScript. This course from Dr. Radu will teach you how to build software solutions from the ground up using first principles. You will learn how to identify subproblems, how to prioritize them, and what to do when they are interconnected. All algorithms will be implemented from scratch and explained step by step using simple language and visuals. So this course is perfect for beginners to sharpen their skills. The focus is the problem of vision-based positioning systems because it has many layers. And this course is offered by Karolia University. Check the description for how you can register for university credit if you get in before the end of October 2025.
Hi, I'm Radu, and you may remember me from such things as the self-driving car no libraries JavaScript course, or the no black box machine learning course in JavaScript. And I just finished painting my balls, so I can teach you something new. You see, I put them to the wall like that, and used this pen with a camera on top to draw some secret things. Question is, can we reconstruct those drawings just from the videos? Spoiler alert, yes we can. Now, during the summer, I organized this as a competition, and everyone did amazing work. You can find all of it on my Discord, the discussion, source code, anything you want. And in this course, we'll study this problem, but my goal is to teach you how to solve difficult problems like this in general. I chose this one to focus on because it has many layers. It can be broken down into many smaller problems using the right techniques. I'll teach you how to identify these subproblems, how to prioritize them, and what to do when they're interconnected, how to isolate them so they can be worked on independently, and how you know if you did it correctly or not. These things took me literal decades to learn, and I'm grateful for all the guidance I had along the way, but I wish there was a more structured way to learn all that. That's why I'm making this course. Now, there are experts out there who can solve this problem by adapting an existing method. They master the terminology, the techniques, and practice them every day. In this course, we'll take a different path, building our own solution from the ground up using first principles. The goal isn't finding a quick fix, it's developing a thought process. Learn to use simple reasoning and the math you know from school to tackle tough problems. We'll explore different approaches, first by hand, then by automating the steps with simple but powerful algorithms. These will be implemented from scratch and explained step by step using simple language and visuals. So this course is perfect for beginners who want to start thinking like those experts from earlier. And the things we study here are used in the real world to solve many important problems. I give examples during the course, so you realize you do become more capable while playing with this silly thing. I use JavaScript because it's easy to get started. You probably have the tools already installed. The syntax is easy for beginners, and it's good at visualizing things in the browser. And if JavaScript really isn't your cup of tea, just use your favorite language to follow along. One more thing before we start. Just listening to me is not enough. You may think you're learning because what I'm saying makes sense, but things tend to come in one ear and out the other. So I really hope you follow along, pause the video to think when I ask you to, and do the homework assignments. Do me a favor and take your time with this one. Maybe even experiment in the real world. Paint your own balls. There's so much you can learn from doing that. I typically end my intros with some kind of joke, but I couldn't think of any this time, even asked ChatGPT, and no luck. So let's just begin. Before we start coding anything, it's important we understand the problem and think how to approach it. On my website, you can find a link to the videos I recorded. The drawings were secret in the beginning, but to make the problem more approachable, I told everyone the first is a circle. The website also explains the setup with the virtual demo you can play around with. The balls are all the same size, but have different colors. These two are horizontal, and together they all form an equilateral triangle centered here, at the same height as the pen when held up straight. Every drawing starts from this location, with the camera pointing at the center of that triangle. After that, crazy things can happen. Now let's play the first video, and we can kind of tell a circle is being drawn, right? We see how it starts moving to the right side and then further back, until about halfway. It's on the other side now, getting closer and closer, back to where it started. But how do we figure this out? Try to analyze and write down your thoughts, as descriptive as possible. Write as if you're explaining it to someone over the phone. Pause the video to do this exercise, and I'll tell you my answer in 5, 4, 3, 2, 1.
I can see the green ball on the right looks bigger than the others, so the camera must be on the right side at first. About halfway, though, the blue ball starts to look bigger, so it's on the left side now. There seems to be a kind of a balance to this right-left motion. I also notice all the balls appear to shrink in the first half of the video, so the camera must be moving away from them. Then in the second half, they appear to grow back to their original size, so the movement seems to loop back to the start. I cannot say if it's a circle for sure, but it's definitely close.
Were you able to write something like that? If not, try again now after hearing Leonard's version. It's useful to have the skill to analyze and explain your thoughts like that, no matter if you talk to yourself, your colleagues, or some AI model. Now, by highlighting keywords, we see those apparent size differences are important. Things that are further away do appear smaller because of perspective. You can see it here. These are all the same size, but this one looks about half as big because it's twice as far. And this works in general. Like, if we know how far away something is in the beginning, and it moves to look a fraction of that size, we can estimate its current distance from us using this formula. We have a good intuition for this, and that was clear during the competition. In the first few days, everyone used the apparent size difference between the blue and green balls to estimate this offset. But to get this other one, they used different things. Minion Toby measured the gap between the balls. Yusuf measured the size of their bounding box. Danny from Denmark used the size of the balls as such and did some more complicated math to figure out the offset. What do you think of these? Would you do something similar? Or do you have a different idea? Pause the video and think what might be good or bad about these approaches. When the timer runs out, I'll tell you my answer. I think what Minion Toby and Yusuf did are the simplest to implement, but they hide a bigger issue. Things are indeed as expected when moving directly in front of the balls, but they get weird when moving to the side. Notice how the bounding box is no longer square, or how this gap is partially hidden by the ball in front. I'm not saying their approaches are bad. I think they can work, but unless we account for those things, they're incomplete, and accounting for them is not straightforward. Danny's approach has the benefit that balls look the same from all angles, and what he does here is more involved, but it's not rocket science. Let me show you using this setup, where instead of balls I have these telescopic rods. They do the math for us. When contracted, they all connect here, at this starting point. The balls appear the same size in the beginning of the video. But if we move to some random point within the video and measure the blue ball again, this ratio tells us we need to make the blue rod 25% longer. And this is how far the camera must be from the blue ball now. But this ball will look the same from anywhere on the surface of this imaginary sphere. That's why Danny used another rod. If we do the same thing for the green one, we must be where these rods connect. They're restricted now to this circle, and if we know the length of the pen, and assume it's perfectly straight and touching the table, there's only one place it can be. Danny ignored the red ball like that, and that was Really clever in the beginning, because he could focus on a simpler version of the problem and implement a quick prototype. He was the first one to get something working, and that's important because he could quickly tell if his idea is on the right track or not. If we start using that red ball now, it just makes that rod fit here like this. It doesn't really affect much in the first video because for the circle I didn't need to lift the pen. In other drawings it will play a bigger role, telling us if the pen is touching the table or not. Anyway, repeating this again and again, we will get a drawing. To demo this quickly, I made a special ruler that measures this size as a percentage relative to the first frame. I also marked the rods like this, showing percentages here too, so I can match what the ruler shows. In this way, I don't have to calculate anything. You could call this an analog computer in some sense. Derek from Veritasium has a video on the topic. He thinks they might be making a comeback. If you want to play with something like this, you can make a quick setup using a simple tripod, like I showed in the first status report of the competition. Now, the math we're doing here is called trilateration. It means figuring out a position by using estimated distances from known points. It's how cell phone towers and satellites can be used to find where you are. The main difference is how the distance to those points is estimated. Here, we look at those apparent size differences. For cell towers, the signal strength is used. It's known to follow something called the inverse square law, so we can estimate the distance using it. Phones only show you the strength to the nearest tower because you don't really care about the others, but it knows those as well and uses the information internally. For satellites, there's a different approach. The signals they send contain information about where they are and when the signal was sent. Those travel at the speed of light, so we can infer the distance using this relationship. I'm simplifying here, ignoring relativistic effects and few other important things, but all they do is make the distance estimate really precise. The rest of the math doesn't change. Now, in practice, more satellites can be used to get a better estimate. Because of small errors, those imaginary rods wouldn't really connect in that case. But if we allow small adjustments, they will, and you'll have a better estimate, one from many different viewpoints. Anyway, I sidetracked a bit, but it's important you understand that these are fundamentally the same problem, because by studying this, it means you also start to understand those other things, which are arguably more important than playing with my balls. That's literally rocket science. It also means what we have here is a working positioning system. It's important because, unlike others out there, I don't have the resources to do experiments in space, and I suspect most of you don't have them either. But with this thing, we can study that same math here on Earth essentially for free. Speaking of math, Danny didn't code actual rods in JavaScript to solve the problem. He could have. A fun thing you could try is using a rigid body simulator and model the rods the same way I did in the real world. But nobody does that because we can solve this analytically as well. We are much slower that way. But computers can do it in an instant. You'll see when we get to that. But now, let's code a quick prototype to see if this idea can be automated in practice.
Coding with Radu. Let's code now.
Have your editor open in an empty folder, and let's create our first file. Index.html. This is going to contain basic HTML structure, so starting with the doc type and the opening and closing HTML tags, and inside let's add the head section with the title, Decoding the Drawings. Let's test the file by opening it in a browser. I'm using Google Chrome, and it's empty for now, but you can see the title appearing here in the browser tab. To add things to the page itself, we're gonna have to use the body section. And we're gonna need a video element. I'm gonna give it an ID input video, and a way to select which video to play in it. I'm gonna use an input, let's call it file input, and this is gonna be of type file, and I'm gonna make it so it accepts only video elements. Now, if you save this file and refresh the page in the browser, you're gonna see this. The video element is actually here, but you can't see it that well unless you open the developer tools, which by the way should always be open when coding. From here you can select the Elements tab, and there you can see the input video and the file input. Nothing happens when you choose a file just yet, because we have to connect the two. We do that using JavaScript. Let's define a script tag, and inside I'm going to take the file input and check if it changes. We'll add the callback function to that, and I'm just going to pass the event here and type debugger. Save and refresh. And now when you choose a file, with the developer tools open, it pauses where we type debugger. And we could inspect this event attribute here. You can see it has a target attribute. And if we scroll down, we're going to find files. It's a list or an array where the first element is a file. It has some information here, like how big it is, when it was modified, and so on. So in our code, we're going to have to do that. We're going to have to reference the file from where we found it by debugging. And now I'm going to pass it to the input video source in this way. And then the video can start playing. Now save and refresh, choose a file, and you can see what this create object URL does is assigns the source to this cryptic looking address. I'm not going to go into the technical details here, but basically it uniquely identifies the video on our computer. And then it starts playing. The reason it's not playing is because the debugger is paused at the moment, so we can press F8 or here to make it go. And there it is, the video playing. Now we're gonna start processing this video, looking at the individual pixels, and for that we can't use the video element as such. We're gonna need to work with the canvas. It has functions that let us do that. I'm gonna define this input canvas here. And we're gonna have to set it the same size as the video itself. We can do that only after the video has loaded. So we're gonna listen for that event and pass a callback function here like so. We can now set the input canvas width to the width of the input video and do the same thing for the height. And after that, we are going to begin a loop where we're going to draw the video again and again over the canvas as frequently as possible. That will happen in its own function. I'm defining it here. And to draw on the canvas, we first need a reference to the context. The 2D drawing context that we can use to draw an image coming from the input video at 0, 0. And then to loop, we are going to call request animation frame, and we pass this loop as a parameter here, and it's going to call itself again and again many times per second. It tries to do it 60 times per second, but if this processing takes some time, then it could lag a bit. Now, we don't need this debugger up here anymore. Let's remove it, save, and refresh. Choose a video. And you can see now the canvas playing, same as the video pretty much. And the canvas does have the same size as the video. You can check these properties here in the Elements tab. Now we don't need the same thing showing twice, so we can actually make the video invisible using CSS. I'm going to go up here and type inline CSS, basically giving a style and setting the display to none. Save, refresh, choose a video. We see only the canvas there. The video is in the memory, but it's not appearing there on the page. Now this canvas here is quite big. It doesn't fit on my page nicely, so we can also make it smaller with CSS. And when adding more and more styles to the page, it's not a good idea to do it directly in HTML like this. We do it in its own file, like style CSS. and link it here, like so. To create this file in Visual Studio Code, you can control-click it. And now we can write canvas, and to the canvas elements, we are going to set the width to 400 pixels. Now save, refresh, choose a video, and we can see this canvas smaller there. But it's important to note that the original size is still that of the video. We are just making it seem smaller so it fits nice on the page. Now separating the code into files like this is what we should do for the JavaScript as well, otherwise it becomes unmanageable. So let's type here a script referencing main.js. Control-click this to create the file. And I'm going to take the code from here. Inside here, save, and it works same as before. Now we're going to start doing image processing to segment the image and isolate my balls there. We're going to do that on a separate canvas, and I'm going to be specific here and say that this is the input section, and down here we're going to do the segmentation on a canvas with the ID segmentation canvas. So we're going to get the input pixels from here and display some kind of output on this other one. Now if we save and refresh, we're going to see this section here, and the canvas is there, it's just transparent. Let's go here and add a style to make these more clear, even if they're empty. A background color and a black border. And we can see it here now. But it's not the same exact size as this one. So we can go to main.js here, copy these, and edit to say segmentation canvas, width and height equal to that. Save, refresh, and now these dimensions match, so we can start working with the image data. After the image is on the input canvas, we can get the data asking the context for it, starting at 0, 0, and all the way to the canvas width and height. And let's log this image data into the console. Save, refresh, and in the console here, you're going to see a lot of these prints happening. Let's focus on this one and see it has the information about the image, like the width and height, and then this data attribute, it's a long array of numbers. This is the same as the width times the height times 4, because these numbers come in groups of 4. Now this is nested here, but it's really just one long array of numbers. And each 4 correspond to 1 pixel. The red, green, and blue component, and this is the transparency. But all pixels in the video are opaque, so they will all have this maximum value of 255. And to understand pixels better, we're going to use a microscope. You see, this is what we get here in the gray area. They are actually a little bit bright, all components, but if I move this over the red ball, you can see a huge difference. And then the green ball and the blue ball, you get the point. Now, before we do the segmentation, I don't like that we have to type input canvas like this everywhere. So one trick you can do in JavaScript is you can destructure here to get just the width and height attributes of the input canvas. And then here, use this width and height everywhere. Now, we don't need this log. Instead, we are going to segment the image, and this is a function that we're going to have to implement, maybe here at the bottom somewhere. Let's say segment image with the image data. First thing we do, I'm going to destructure again to get the width and height and the data from the image data so that I don't have to type image data dot everywhere. And then I'm going to take the context of this segmentation canvas so that we can display some processing on it eventually. Now the output data, I'm going to define it as a new image data with this width and height. And we're going to loop the original data coming from the input canvas like so. I'm going to skip here 4 by 4. And now I can access the red component like this, and the green component like this, the blue component like that, and the alpha component like that. And if I want, I could set this output data to these values starting at the I index. And then let's put this output data starting at 0, 0 in this segmentation canvas just to test. Now save and refresh, and it's basically cloning the canvas at the top pixel by pixel. But we can do more things now. Like, for example, you could replace here this G and B with R and R. And what we get now is the red channel. So white here means there is a lot of red, and black should mean the rest. But because this is not pure black on the background, it has a little bit of red in it. My other balls are less red though. Anyway, let's check the green, and we should expect the same kind of output, right? Save and refresh, and it's not as similar at all, is it? I mean, the green is still quite bright, but not as bright as the red was. And these are actually brighter than the background, like there's a lot of green in them, especially in the blue one. I'm always surprised by how counterintuitive this feels. Like, looking at the image above, I would say that those are green and red and blue and in the same amounts. But the computer thinks otherwise, and we're gonna need to account for that. Let's check the blue as well. Save and refresh. And it's more like the red, for sure, than what the green was there. So now the idea to segment the balls from the background would be to threshold somehow to keep just the pixels that appear more bright in these individual channels. We do that by adding a threshold here. I'm going to set it to a parameter with the default value. Let's just say 100 and see how it works. And here, after we get those original values, I'm going to define new values for red. If the original value is greater than the threshold, I'm just going to set it to 255, the maximum. Otherwise, 0. And I'm going to do the same thing for green and blue. So G, G, and B, B. And this is going to be now new R, new G, new B. We're not really using this alpha, so I can remove it from here and just type 255 here. Now save, refresh, and it kind of works for the red ball and the green ball, but the blue and some green combines because of what we saw previously, blue having some green in it. And that's going to be kind of hard to fix. We can play with this threshold more, like let's say put it 150. And now the blue looks okay, but the green starts disappearing from here at the bottom. We can try going maybe 125. And it's better, but still somewhat disappearing from here. Can try 110. And you're going to see that it's either one thing or the other. We're going to have to be a little more clever here. Let's inspect that green again. So the problem is there is quite much green here, but there's much more blue. I mean, look, if we take the microscope and check it out, blue is much more intense. So how about we calculate the difference? Like, maybe we go here and say a difference for green is green minus, let's be general and say red plus blue divided by 2. I'm gonna average these out. And now I'm going to pass this difference here to visualize. You can see that we get a much better result. So we can do the same thing for the others. Let's say a difference for red and a difference for blue. And now here we can check this red difference, green difference, and blue difference, and pass these values as before. So the new red, new green, and new blue. Save, refresh, and we still get a little bit of a problem with the green, but now we can just lower this threshold more, like maybe 80, and yeah, this looks pretty good to me. Next, we can measure how big these balls are by counting how many pixels we detect in each of these colors after segmentation. We can prepare an array for those, let's say RGB counts, and set each of them to 0. And now here we can say, let's increase this value by new red divided by 255. So this is going to give us 1 or a 0 essentially. And we do the same thing for index 1 and 2, or the green and blue values. And at the end here, we can return these RGB counts. So now here, when we call segment image, this function returns something. We can get the value like this, and let's log it in the console to test. Save and refresh, and this is the number of red, green, and blue pixels on each frame. They change all the time. These values are like the signal strengths in that cell tower example. You can think of the signals as how much light is reflected by these balls, and the camera is the sensor picking it up. These follow the inverse square law, so we could think of it in this way too and end up to pretty much the same thing. But let's stick to the original plan and calculate the width. Now, circles are more commonly represented by their radius, which is half the width. And in practice, it doesn't matter if you use the whole width or half the width or a quarter of the width. When calculating that ratio, scalars like that simplify. So let's use the radius because it's the easiest to get when we know the area or pixel count. The parent radii are going to be calculated from these RGB counts. And in JavaScript, we could use the map function for that. It takes a function as a parameter that says what to do with these areas. So in this case, we want to return the square root of the area divided by pi. We could also use a normal loop or do this calculation 3 times for each of those counts. But I want to show you the map because it's very common in JavaScript, and it can shorten things quite a bit. Actually, this can be made even shorter because JavaScript also supports something called arrow functions. So we can just say that this area parameter turns into the square root of whatever our function is. So we can write this in one line like so. And if we debug now with this apparent radii, we can see that these numbers are much smaller now, like around 100 pixels. Let's remove this log. It won't be needed anymore. To visualize the setup, we'll need to know the positions of all these things in a coordinate system. But there isn't one. So we need to decide where to put it. And that's the question, where do we put it? During the competition, some chose this point to be the origin. I think it's because of the symmetry. But James used one of the balls instead. That can also make sense. There's even a real physical object there marking the place. And as he pointed out, it can make some of the math easier. I'll show you later. Now, I will choose this point because then the drawings are 2D essentially. The pen can only go up in this positive direction, and there's also a symmetry here like I mentioned earlier. Now, for the orientation, we also need to make a choice. My favorite is this one because the drawings would be on the XY plane. But this time I'm going to go with AOSAS because it matches the default in Three.js, and that will make some things easier later. I'm also choosing it because he won the competition, so you're welcome. In principle, any one would work, and there are pros and cons to each of them. But putting some thoughts into it may mean you make the problem easier, so it's usually worth it. Go to the top to define some global values. Like the ball radius, it's 3. The distance between the balls is 9. The pen height is 18. The initial Z offset is 18. And we can use these to calculate the initial camera position. I'm gonna make this as a 3D point with X is 0, Y is at the pen height, and Z is the initial Z offset. We can also calculate coordinates for the balls. I'm going to solve them in a separate function because this calculation is more involved. And let's just implement this function at the end here for now. We're going to refactor things later, but first it's important to get our idea into the code, and we worry about refactoring later. Now this initialize balls function really is going to work with that triangle as the basis. So the length of the triangle is the distance between those balls. And now we can already calculate the left and right offsets. Like the left is minus this triangle length divided by 2, and the right is plus that triangle length divided by 2. And now we also need the height of that triangle. And we can get it using a formula you learn in school. It's just a consequence of the Pythagorean theorem. In this right triangle, we have the height squared plus half the length squared is equal to the full length squared. Rearranging, we find the height like so. This reminds me of school when my friend Tino used to say that if right triangles are around, there's nothing to worry about. That stuck with me, and I'm telling you this because it can give you confidence in the right moments. Now there's another right triangle here, and it's similar to this large one because these angles are the same. So these ratios are the same, and from there we can figure out how far the bottom is from the center point. We can write this simpler in terms of the height length, so bottom is 1/3 of this length downwards, and top must be what's left, so 2/3 of that length upwards. Most of the math we'll need in this course focuses on these right triangles, so it's really important you understand them well. If you had trouble following what I just showed you, I recommend you take a step back and check this video out. In it, I explain the Pythagorean theorem in an intuitive way and show you a way to prove it using similar triangles. Now I'm going to take out the radius here from that global variable and use everything we got to define 3 objects with X, Y, Z, radius, and color. The first one is going to be the red. The second one is going to be the green, storing here these ball properties, essentially. Let me arrange this a little bit nicer so that these align. I think it makes the code much more readable. And now to visualize all of these properties, we're going to go and create another canvas. It's going to be in an output section. Output canvas. And now we have to specify here how big we want it to be, because this is not depending on the video. And back inside of the main, I'm going to implement a new function to draw on this output. So draw output. Let's get the reference to this output canvas. And now loop through all my balls. Take out from there these important properties that we are going to use. And begin to draw a circle. And then the arc is more general, and we need to specify that we want to start at the 0 angle and go all the way to 360 degrees. But like pretty much all functions in JavaScript that have to do with angles, they use radians, so 2 pi. And now let's set the fill style to that color and fill. I'm also going to go here and draw the initial camera position for reference. So I'm going to take out the x and z from this global variable. And let's use the arc again. I'm just giving it a radius of 2 there. And black color and fill. Let's call this function at the top after we have the balls initialized. Save, refresh, and you can see the output here. Kind of. These small things are the balls, and the initial camera position is there. So these values are in centimeters, the way I measured them. And now 3 pixels is like nothing. So these values appear very small. And I have seen during the competition, some people try to scale these up, like maybe multiply by 10. That would still give kind of a small values, maybe multiply by 20. Problem is, it starts to be confusing. Where do those numbers come from? So I like to keep these as such, and then go where we are working with the output and scale it somehow. I also want to move these to be somehow in the center screen here, because now we just see part of the setup. So for that, we can use these helpful methods. The translate can go to the output canvas width divided by 2 and height divided by 2. And to scale, maybe we just use 5 for now. Like, let's see how it looks like. Save, refresh, and the top view already looks nice. Actually, it's a bit confusing because from the top, the red ball should be the first we see. Maybe we do this loop in reverse. So starting at balls length -1, greater or equal to 0, and I minus. Save and refresh. It's better like that. But actually, I think we said we work with the simpler version of the problem. So let's remove the red ball from the visualization for now. And an important thing, every time we work with these functions, restore the canvas so we don't forget it in this kind of transformed state. So I'm saving the state before doing this and restoring now. It won't do any difference at the moment, but when you call these functions many times or in a loop, then problems start to happen. So I always remember to do this. And to make things clear, we can also write here that this is supposed to be a top view. I'm gonna do that before we start transforming things. So let's just say top view, and I'm gonna give it a small margin, maybe 5. And the text is actually cut a bit because of how the baseline is by default. I'm going to tell it to use the top. It's a little better, but kind of small. So I'm going to set the font to 20 pixels Arial. Okay, I think this works. And one more thing that could be improved, I think, is the contrast between the background and these is not that great. Some people might have issues seeing them properly. Let's set the background to white by drawing a white rectangle over everything. So we need the width and height, and let's destructure here so that the code becomes even better. So I take them like that. We don't need this here anymore. And at the top here, we start off by setting the fill style to white and filling a rectangle the whole size of the canvas. And we remember to set the fill style to black again, otherwise this text is not going to show. And now it's better, I think. Your first homework is to figure out the initial distance to the balls using geometry in this triangular pyramid. Scribble down how you got the answer and implement that formula in the code. You'll know if it's correct if the result matches what I'm going to show you next, because I'll solve the problem in a different way, using the Euclidean distance. It's a way to calculate distance between points. We know their coordinates, so we can calculate these lengths and use the Pythagorean theorem twice to get the length of this diagonal. If you want to learn more about it, including how it generalizes to higher dimensions, I have a video on the topic. But I won't insist on it because JavaScript has a way to calculate it already built in. We will store this initial distance to the balls inside of a global array. So we store 3 values, one for each ball, and we can use the map again. So for each ball, we're going to return here the distance to the initial camera position. Even though this distance is the same to all balls, so we could use just one variable for it, I'm using 3 because it makes the system more general. If at some point we have a different setup, then it's going to work without any other changes. And this distance function I'm just going to add here at the end. From 2 given points, JavaScript has a function for calculating the Euclidean distance. So we are done. Save and refresh. We can debug here in the console if we start typing that and see that the initial distance is 18 point something, which is a little bit more than the 18z offset. So it looks okay. We can also visualize these by passing them to the output. I'm going to take here this, pass it to the output because these are going to change eventually. So they should be a parameter here. And what we'll do is inside of this loop going through each ball, I'm going to copy this and do the same thing, but with this distance to the ball, I'm taking the component associated with this same ball. And then here I want just to draw the outline of the circle. So stroke style and stroke. Save, refresh, and there we have it. These lines are a little thick. Maybe we can set the line width to 0.2. And this dot is actually quite thick also. So maybe we make it 0.5. Okay, much better. And now we're ready to estimate the distances when the camera moves from there. So we'll need to know how big these radii are in the beginning, in the first frame of the video. And I'm going to store this information up here in initial apparent radii. Let's just set it to null. And the first time we get some radii, I'm going to set that value. So if that value is not set, it's going to become those apparent radii, like this. And now the distances to the balls, just an empty array. We're going to do a simple for loop going through those apparent radii, like that, and calculating that ratio. So what it was in the beginning divided by what it is now. And the distance is going to be the initial distance that we calculated multiplied by this ratio. And now we can pass these to the draw output function call. But we have to take it from here. I'm going to remove it from here and just paste it here inside of our loop. So it updates on each frame with these new values. Save. And now if we scroll down here, we see these circles changing. This initial camera position is still showing there for reference, but you can kind of see this intersection point moving almost in a circular pattern. And now it's going back. Yeah, I can already tell we're on the right track. Creative coders might be thinking now that, hey, those green and blue pixels are close to each other. Maybe we can look for that in the image, and yeah, it would work, but it's slow processing all those pixels. And you don't really get the most accurate result since you're limited to whole coordinates. We can solve this analytically in a number of ways, like the circles can be modeled using this circle equation. If you want to understand it well, I have a video on the topic, or you can play around with Desmos. I made a special page for you to try out. This equation describes points on a circle, and you can control the center point and the radius. Now, if we have two circles, they might intersect like this, touch, or do none of these things. If you solve this system of equations, you'll either find two solutions, one solution, or no solutions, depending on which scenario you're in. Your second homework is to tell me which one is it. Find the x and y for these, and then consider these as parameters to get the general formula for x and y that we can use in the code. Meanwhile, I'll show you a geometric way to solve the problem, the same thing James did during the competition. We're gonna go here after we measured the distances to the balls. And I'm gonna use the same naming as in James's diagram. So A is going to be this distance between balls. B is going to be the estimated distance to the blue ball, and C is the estimated distance to the green ball. Using the Pythagorean theorem in this right triangle, we can write z squared to be this. We can also use the Pythagorean theorem in this other triangle and write z squared to be this other thing. Now these have to be equal. We can simplify to get the final value for x, equal to b squared minus a squared minus c squared divided by 2a. Now x is known, so we can use it to get the z value. Just type z is the square root of c squared minus x squared. And these are our camera position in this 2D simplified version of the problem. Let's pass it to the draw output function call here and update our draw output to have this camera position as well. So instead of this initial one, it's going to change. Save, refresh, and we can see here there is a kind of an offset to where the circles actually intersect. Now, this works for James as such because he chose his coordinate system centered on this ball. In our case, it isn't, so we have to account for that. And this is what I meant earlier when I said that sometimes choosing one coordinate system over another leads to simpler math or other benefits. In this case, I have to do more math to compensate for that. So adding here an offset. Save, refresh, and now you can see this dot is exactly where the circles intersect. Now this is almost the same thing I did with those rods in the beginning, with one small difference. This 2D simplification forces the rods to connect here, at this level. It means the pen gets pushed back slightly because the distances were estimated in 3D. It's not a big difference, so let's not bother with it now, but we did notice it, so we do make a note of it. Maybe at some point it becomes important. Let's collect all of these positions that we find and draw a path. So I'm going to go here at the top and say camera positions is an empty array. And every time we get a new one from this calculation, I'm going to push it to that array. And the output now is going to get this instead of just one position. So maybe we just call this path since it's going to look like a path. And here I'm going to loop through that path. And I'm going to use a for each loop just to teach you that these exist as well. And sometimes they can make things easier to read. They are actually a little slower than the normal loops, so be careful with that if you're looking for efficiency. But I don't care much about that in this video. Now here we can get the x and z from this point directly. Or we could write x and z directly here at the top and remove this line entirely, but x and z need to be wrapped in parentheses to look like a single thing. And you can see the path appearing there now. We now have something that looks promising, so what do we do next? Make a choice. Pause the video and make a choice. It's a really important decision. I'm gonna tell you my answer, so get ready for that. I know it's tempting to start analyzing this and figure out how to improve, but in that way, this spaghetti code becomes even worse. And then you're gonna be tired, and you'll leave it like that. Even if you're the only one working on this project, you will forget many things about it before you open it again. And if you leave it in this state, it's gonna take forever to get back up to speed. Fact of the matter is, now is the time to refactor when everything is still fresh in mind. Now, we won't over-engineer this, just a minimum I think is needed to keep things clear. But if you are interested in software engineering, check out Yusuf's code from the competition. He did many clever things there, like extending classes and other things like that. So to make the code better, we go up at the top here. Notice that all of these are parameters. These globals can go in their own file. So inside of index.html, we're going to define more files here. Maybe parameters.js. Control click creates this in VS Code, and I'm just going to copy from here this. And also the function to initialize the balls from somewhere down here. Now, normally functions should have parameters, initialize balls relative to what, so some of these properties should go in it. But I'm not going to engineer this too much because it's kind of clear that things related to these global variables happen in this file. Now let's save main.js as well and see if things still work. And they don't. Distance is not defined. This is happening in parameters.js now because this distance function that we define in main doesn't exist yet. The order in which you include these is important, and in modern JavaScript you can go around this by using modules and more software engineering stuff. But this problem is really hard as it is, and I'm not gonna introduce those other concepts. So we just have to pay attention to that. And we can create a new file here called math.js and move that only function there for now. Save, refresh, and the problem is gone. Select the video and see that everything still works. Next, let's separate this image processing stuff. So segment image, this function can also go in its own file. I'm going to cut it from here, create a new file here, image processing. More similar functions can go in it, but for now it's just this one. Save. And let's do same for this output. So cut, duplicate this output, paste. Now every time we do this separation, I also check to see if there's something I don't like about this code. Like now I see all this kind of duplicated stuff happening because drawing a circle essentially in slightly different ways. So maybe we can take out the function, a helper function for drawing a circle on a context with these properties. And then we're gonna just call this function there instead. So simplifying the code and making it more readable. This is gonna be a generic circle drawing code. setting the fill style and the stroke style. And now we have to check, is there a fill style defined? If there is, we can call ctx.fill. In modern days, and not just JavaScript, but other programming languages too, we can do something like this. So it will evaluate fill style. If this evaluates to true, then it considers what happens next in this and. If this would evaluate to false, then it doesn't consider this part anymore. So it's like it doesn't exist. Of course, you can write this using if conditionals, but I want to show you this because it's common and it can help you out if you see it somewhere. So calling this draw circle now is gonna remove quite a lot of code. We can say here draw circle ctx_xz radius color. And here we can say pretty much the same, but after xz we pass the distance to that ith ball. And then no fill, so null, and the same color that we used here. And here we can just say draw circle 0.5 black. Now, because this line is the only one here and it's quite short, we can write the whole thing on one line. And we can even remove these curly braces. Like if we remove them and also remove the semicolon here, then JavaScript doesn't complain. And we can just put this up here. I think this is quite clear. So for each element in the path, we take its xz component and use it to draw a circle that is black and has a small radius. Now this is okay, I think. Let's close some of these unnecessary files, and inside of main, it looks much better already. Let's save and quickly test to make sure the changes we did still work. And they do. Great. So next thing is here. After we get these RGB counts, we started being sloppy and just added a bunch of code to this function, making it really confusing. Like, of course, you know what it does now, but imagine you come here after a week and try to remember all the things. It's time to make it clear. So using these RGB counts, we get the radii, essentially estimate the distances to the balls. So it makes sense that that can be a step, like the distances to the balls will come from this type of function. And then when we have these, this part is James's solution to estimating the camera position using the distances to the balls that we just estimated and the ones from the parameters. So another step is going to look something like this. And this is all we need in this loop, really, followed by collecting the positions and drawing the output. So everything else has to go somewhere else. And these steps are going to become very clear what really happens in the loop. We'll create a new file for all this calculation. Let's put it here, estimator, and in it I paste what we had in the main earlier. And here we can start defining those two functions. So estimate distances to balls from a given RGB counts. And let's return here those distances. And the next one, estimate camera position from distances to the balls. And here, return camera position, and remember to close the curly brace. Actually, we can return also this directly, because defining that variable just to return it doesn't make much sense in a function where the name of the function is essentially the same as the variable we just had. And up here, we could look at the math a bit and notice that dividing by pi doesn't really make a difference. It's just extra work. So removing it is fine. And this initial apparent radii, it's not clear where it's coming from, so we could take it here from the top of the main. Makes more sense to have it here where it's being used. Save and refresh, and everything still works. But one thing I don't like is that we always have to keep doing this, like scroll up and down and up and down. And may seem like a small thing, but if we fit this one here on the right, we don't have to do that. And that can save time when debugging. So let's do that. In index.html, I'm going to make a new structure for this. And group the input and the segmentation in a div so that it's going to eventually be on the left side. And then this output goes in another div on the right side. For this to work, I have to tell the body that it should go horizontally. And it's enough to tell it to use display flex this time. That's much better. And since I'm here, I can also change this font to be sans serif because it will make it look more like font here for consistency, and I like it more. There's still this warning here appearing on the right saying that we can get the system working faster if we do this. So let's do this. In main here, we just have to specify that we will be reading the image data frequently from that canvas. And the warning is gone. One thing that is a little bit not so nice is that I see kind of a pixelation here, and one solution to the problem is to just make this output canvas bigger. So maybe we can even double the size, 800 and 140, because everything scales to 40 pixels in width. This is just going to increase the pixel density. So the result looks like this now, and it's now too small. So we can go back to the output and essentially double these values. So 40, and when we scale, let's try bigger. I think the circles could be a little bigger there, maybe 15. Okay. And I think these lines can be a little bit thinner. This thickness can be smaller as well. It's important you do whatever you feel looks nice, because then you become attached to this software, and it's more likely you're gonna keep coming back and improving it from time to time. It's a psychological thing. We have a result, and it does look a bit like a circle. Now, I've seen many people in this kind of situation try to fix it by processing the output in some way, maybe averaging or some kind of smoothing, but the best problem solvers look for the root cause instead. Pause the video and think, what can be the reasons it looks like that? Think while looking at the video a few times. Give it a while, then come back to see if it matches what I got. My list looks like this. Do we trust my drawing skills? Is it really a perfect circle? Maybe that's just how I drew it and it's perfect already. What if I didn't put the balls exactly at those coordinates? Maybe small errors like that do matter. Why does this ball look like an egg? Shouldn't they be circles? The pen is not always straight. Sometimes the image is blurry. Look at the sides here. Balls can sometimes look bigger because of that. And if you think about it, earlier when we did the segmentation, the green color was weaker than the others. What if the sides blend in unevenly because of that, making this one look smaller? Let's add that one from earlier, that the pen is being pushed back a bit, to this list, and that's all I got. Do you have something else on your list? Let me know in the comments and add them next to mine to make a bigger list. There's no harm writing many things here. Maybe some of them are indeed nothing, but it's only a problem if we start working on the wrong things first. Like, there's no way fine-tuning the segmentation will fix these big issues here, right? So what we'll need to do is prioritize things. Pause the video and sort them by what you think is the most important. We can't be sure of these, but we can speculate. Now, my list looks like this. These things, we don't really have a way to know how big of an issue they are. Maybe it's all my fault and the others don't matter much. You could try to make a similar setup and draw more carefully than me to reduce some artifacts. But it's hard to get rid of all of them, trust me. Because you have to draw while also making sure the balls are in frame, not making too many sudden movements. Unless you have a robot arm or something, it's pretty much impossible. But what we can do is simulate. A clean simulation will give you the best possible outcome. Now, getting it to look exactly like my videos, matching my camera parameters, was seen as a downside during the competition, and very few people tried it. I think we do this simulation to better understand the problem, not to model my camera perfectly. And if the simulation lets us control some settings, that's great. It would be very expensive to do that in the real world. Many companies rely on simulations because of that, so learning to build one is valuable in many different situations. Another reason people didn't try to simulate is they thought it's too much trouble and probably not even worth it. Maybe it's my fault because I bragged about how accurate I drew those things, but anyway, let's see if it will be worth it and if I can change your mind. There was one person who did make a simulation. Bas even took first place for a while, and I suspect he could have even kept it longer if wanted. Anyway, I'm a bit sad no one even tried to use his simulation. I even demoed it in a status report, and I think it could have helped everyone better understand their methods. Now, to build a simulation, we'll use Three.js. We don't necessarily have to for a simple scene like this. We could just code a 3D environment like I showed you in the self-driving car course or my Slenderman Halloween livestream. But I want to get this done fast to show you that it's not too much trouble. Three.js is also popular when making 3D games or animations, so practicing it means you're gonna level up those skills as well. Think about it. Game characters have positions and rotations like the balls and the pen. Many things there are the same as here, and that's why I think Bas did it so effortlessly. Now let's learn to do it as well. We'll add the simulation as an alternative input here next to the video. For that, we're gonna need another canvas. I'm gonna define it here below the input canvas. Simulation canvas, and I'm gonna set its width and height to match that of the videos that we're working with. I'm trying to get the simulation as close as possible. Now we're gonna implement this in its own file here, just before main. Let's call it simulator. And the quickest way to use Three.js is to paste here this link. It's gonna load it from this address. Now Control-click to create simulator.js, and inside it we're going to define a renderer that is going to be set to work with this simulation canvas. Now if you save and refresh, we're going to get here a black canvas. Without this line, the canvas is just transparent. So this is how we know that Three.js is working. And we can begin to define our scene. Scene is a new 3 scene. And we can add balls into it. We can loop through that global variable. So each ball is going to become an object that Three.js understands. First, we need to define the geometry. So we use this sphere geometry where we pass the radius and 2 other values I'll explain soon. And then we need the material for this. We're just going to use a basic material and set the color to be that from the ball, like that. And to see it, we need to construct a mesh using this geometry and that material. Now we set this ball mesh to the position we get from those global values. And now we can add this mesh to the scene. And next we need the camera. I'm gonna define it using a perspective camera, setting an FOV to 75, and the aspect ratio, I'm just going to calculate it here from this simulation canvas, width divided by simulation canvas height. We set the camera to be at the position coming from the initial camera position in our global values. And the last thing we need to do is render the scene from this camera's viewpoint. Now save, refresh, and this is what we get. It looks familiar. Now, if you choose a video here, you'll notice that the balls look a bit smaller than the first frames of the video when the camera is in that initial camera position. This is because of this FOV. If we use a different value here, like 60, you can see they are bigger and more closely to what is in the original video. I'm going to set this as a global here in the parameters file. So the camera FOV is 60, and this is just a guess. I'm not optimizing this in any way now. And I'll use this value here, like so. Now the balls also don't look very circular, but that's because of this parameter here. Let me show you using a wireframe here in the material. So this is how 3D balls are generated, and these are numbers of segments. So we can replace this with higher values, like maybe 16. And when I refresh, you can see more detail appearing here. And we can go all out, maybe 128, just to make sure that these do appear to look the same from all angles. And they almost look like solid objects, even though we're only showing the wireframe. So let's remove it. Yeah, and if you look really closely, you might see a little bit jagged edges appearing here. We can get a better result by turning anti-aliasing on. So here in the renderer, we can also specify to use it. And if I'm gonna refresh now, it's a little better. Now we're ready to animate this, make it move in a circle path. We're gonna create this path using a function that's gonna start with this initial camera position. So I'm gonna implement the function down here and say we generate the circle path from this starting point, and the circle path is gonna have a radius, let's just say 10 for now, and the point count, which basically controls how fast the animation is going to be, let's just say 100. And now these points that are going to be generated are going to go in this array. And when working with circles, we should have access to the center point. So that's going to be the start point shifted in the Z direction by the radius. And now we can loop. So we can go and generate all these points by first measuring the angle. It's going to be a fraction of this. And now we have to scale between 0 and 360, or 0 and 2 pi, because most of the things in JavaScript work in radians. And to get the x and z components, we are going to take the center x, add the radius times the cosine of the angle. And the z is the center z, plus the radius times the sine of the angle. The y just stays the same. So I'm going to keep it like this. And now we can add this xyz object to the points array. and we can return it. If your trigonometry is a bit rusty or you never understood it well in the first place, I have a video where we learn these functions by making interactive visual explainers. I think by coding those you understand much better than with pen and paper. You'll also learn what functions JavaScript and most other programming languages have already built in to help you out. We'll need to use more trigonometry later in the course. If you ever feel like it's too much, don't give up. Just check that video out, I'm sure it can help. We're also going to need a function that updates this simulation. So maybe here, that moves to the next point in the path and so on. So the camera has to move to the next position here. And I'm going to say copy, shift the path. That gives us the first point and also removes it. And we also want to render the scene, so I'm moving this code inside of this function. And this is the function that we need to call inside our loop. So in main.js, the loop is tied to the video at the moment. So I'm actually going to comment everything here out until this part here. So we get the simulation working. And in it at the moment, we just update the simulation. And I'm going to call this loop as the page loads, so I'm not going to press any button for it just yet. And now if we save and refresh, we see something happening. Now the camera starts on the right side of the balls instead of just in front. So we need to go back to our simulator and subtract here 90 degrees or half pi. And now if we save and refresh, it looks like the same motion from my video. There's an error appearing here, but it happens at the end and is not really disturbing us in any way. So let's just ignore it. And here inside of the main, we want to get the rest of the functionality working with this simulation data. So what we would need is this kind of image data object coming from the simulation. If we could get it in some way, like maybe something like this, then the rest of this code can just proceed. This 3D canvas doesn't have a way to get the image data directly, but we can implement one ourselves. And to implement this function, we can go back to the simulator, and it's going to be a bit more technical, but I think you can manage. So the first thing we do is get the width and height of the simulation canvas for easy access. And now we're going to define a pixels array. We have to use this uint8 clamped array. The size of the width times the height times 4. You probably know by now why this is needed, but the type of the array is needed because otherwise the functions inside of the Canvas API won't work. So we just have to do it. Uint just means unsigned integer, 8, it's an 8-bit integer. Clamped means the values shouldn't escape that range and they won't. So it forces them not to. I don't want to get into details like that here. It just has to be that way. So now we can get the context from the simulation canvas, and we get the WebGL context this time, so not the 2D one. And it has a function to read the pixels. Starting at 0, 0, given the width and height, and now some more parameters that just have to be there. Like that we use RGBA and that we have an unsigned byte here. A byte is 8 bits, so it kind of makes sense. And the pixels. So this pixels array gets populated with the information that this WebGL context gives us. And now the image data, we can create a new image data with this pixels and the width and the height, and we can return it. Save and refresh. And it's so... Why is this so oval? And why is it going the other way around? I mean, we defined the circle to go that way. We're basically estimating the complete opposite. Okay, time to focus and finish what we are doing at the moment. I know it's tempting to look into this, but there is still very much to be done here to support both inputs. And why is the segmentation canvas not showing anything? I think it's because it's not set to the proper width. So let's go here and set it to be the width of the simulation canvas. And we do the same thing for the height. Save, refresh, and it's upside down. Maybe that's the reason why this goes the other way around, but it shouldn't, because our solution so far doesn't know where the balls are. It just knows the size they appear, so putting it right side up won't make a difference. But the reason it's upside down is because those coordinate systems are different. We should flip it so everything makes sense, right? And we can do that a number of different ways. We can use some tricks to work with the canvas, scale with negative values or whatever. I'm just going to go the old classic way and flip these pixels one by one. So I'm going to add a comment here because it's really needed. And we're going to loop in the top half, like this. And now for the X as well, all the way to the end. And for each pixel, we're going to have to update all the RGBA components. So I'm going to do a loop here from 0 to 3 with I. And now let's get the index on the top side. It's going to be Y times the width plus X times 4. And now we add I. We're going to have to swap the pixel value at this index with the symmetric one on the bottom half. So maybe first calculating the Y of that is going to make things easier. And now the bottom index formula is basically the same, but with this bottom Y instead. And to swap, we're going to need an extra variable. Let's just set it to be the top index. Now we replace the top index with the bottom index, and the bottom index is going to be box. Now if we save and refresh, this image data looks as expected. And the segmentation looks pretty much the same as the original because the original is so clean, it's already segmented. Anyway, the simulation now starts automatically, and I would like to select whether I want it to start or the video. So let's add the button for that. It's going to be here after this file input. Let's say simulation button simulation. And now in main.js, I want to be able to set what is the input type. So maybe input type is null in the beginning, but now when we click this simulation button, let's put this code inside that. And also set here the input type to be the simulation. And here where the video starts, I'm going to set the input type to be the video so we can tell them apart. This is going to be important because here in the loop, we have to support both of them. So if the input type is a simulation, then this code goes there. Else, if the input type is video, and maybe we could use a switch here, but it's just two things, so it's all right. Then this part of the code happens. And this image data has to be at the top. So image data is null, but now depending on which of these input types is here, we're going to populate it this way or this way. And I realize now this input canvas name is not so good because both the simulation and the video are inputs. So maybe calling this video canvas is better. Video canvas, and replace all. And let's go to index.html. Replace this one as well. Now if we save and refresh, the simulation button is here. Pressing it starts the simulation, and choosing a video starts the video, and it seems to work. We can see now the different shapes appearing there, but they shouldn't mix. I mean, this is very confusing. So I'm gonna make the video canvas disappear if we start the simulation. And if we start the video, I'm gonna make the simulation canvas disappear. And actually, what's also confusing is this first start page. I mean, so many different things, they're all empty. This is what the user is expected to press on, but it's somewhere in the middle of the page. We should keep these as the only thing they see in the beginning. So let's go back to index.html, and here at the start of the body, I'm going to implement a start panel. In this, we're going to put the file input and the simulation button. And the rest of this is going to be our main interface. And I'm going to set its style to be invisible. Align it better and close this div. Now, this main interface is going to become visible, and we'll do that here when the input video has data. So when the video starts playing, we'll also make the start panel invisible. And I'm going to copy this because the same thing has to happen also when starting the simulation. Save, refresh, and this is better. So the simulation starts the simulation. And this, select the video, starts the video. Good. Now, if I look at the start page, I see here choose file, no file chosen. Maybe the simulation has something to do with this file. Of course, we know it doesn't, but does anyone else know? And will we know next month or whenever we look at this project again? So it's important to make things clearer. Otherwise, we can spend a lot of time remembering, re-remembering these things at some point. I'm going to add a button that just says video and remove this or hide it, basically. So next to this simulation button, I'm going to put a video button. It says video. And let's hide that file input. It's still existing there. We will use it. So when the video button is clicked, it essentially clicks the file input. And now it's two clear things there. So the video opens that file choose menu, and it still works as before, but this is now clear that there are two options and they're not related to each other. I'd prefer if these buttons are in the middle of the screen somewhere. So in the CSS, we're going to define some style for the start panel. I'm going to give it absolute positioning and left 50%, top 50%. This moves this top left corner in the middle of the screen. So we should also translate with minus half the width and half the height. And now they are centered. And for this main interface view, before we used to have a small gap there. I wonder what's up with that. In the elements section, we can experiment with different styles here. Maybe justify content space between. I think the width should be 100%. Yeah, so these tiles have to go to the main interface as well. Main interface, justify content, space between, width 100%. And now when we refresh, it looks as before. Why is it doing that? Okay, almost there, almost there. Still to do something with this input, because now the input is doing so many things. It really needs to go away from here. It's making this main file so long. So in index.html, I'm going to prepare a file for it. Input.js, control click to create it. And we'll take from the main everything here at the top. Yeah, and then the loop, all this crazy part from here is something that the input should really take care of. So we go to input.js and let's say get input image data. So it's either going to get the one from the simulation or from the video, depending on the input type. And then it's going to also return this image data, like so. So in main.js, we can just type here image data is get input image data, and we can read this file without knowing exactly how it does it, but if we ever need to learn how it does it, it's in input.js. So save, refresh, and simulation. Well, in the video version, I try to point the camera at the center of the balls. Maybe that makes a difference. Well, let's see. It shouldn't, but maybe it does. So in the simulator, after we update the position here, we could also tell the camera to look at a vector with 0 pen height and 0. It makes a big difference. It looks perfect. Or is it really? It looks kind of squished like that. We could ask the simulation to tell us exactly where each point needs to be so we could compare in a better way. So here we could define the true camera position. So this is going to be equal to whatever that point is, and pass this one here and also return it here. And in input, where we do update the simulation, we do the same thing. So the true camera position is null, but here we can set it to be whatever the simulation gives us. And we return not just the input data, but also this other information. And now in main.js, we do the same thing. So here we take out not just the input data, but also the true camera position, like so. And we can pass this to visualize in the output. And the output, we need to update it here to also have this true camera position. And after we draw the path, let's just draw a point. So if the camera position is there, because we only have it for the simulation, I'm going to draw a circle at that X and Z. And let's just make it similar size, but different color. And now save, refresh, simulation. It's not where it needs to be. And if I remove that look at, so we don't rotate the camera and keep it pointed at the wall, it really should be there, but it's on the other side. Pause the video to think what can be going on. Think, why is it so wrong? Take also your list from earlier and see if it helps. Remember to scratch off those things that the simulation solved for us. Well, look at this ball. It's furthest away from us, but it looks really big, bigger than the others. It gets stretched when close to the side like that. When the balls are in the center screen, there's less of that, so things work a bit better when the camera looks directly at the balls. Now, during the competition, several people figured out how cameras work and how to cope with distortion. There were different learning resources being passed around, but not everyone could understand what's going on. And the truth is, some explainers work on some people, but not on others. So let's try to build our own and make it as clear as possible. Cameras are boxes with a small opening in front where the light goes in. Nowadays, there are crazy ones with all kinds of lenses, but I didn't use anything special like that. You can make a simple camera yourself with no lens at all, and you'll see the same kind of stretching happening along the sides because they project on a flat plane. Now, making a 3D explainer for this is a lot of work, and they're not very good in my experience. You need to spin them around until it becomes clear what you're looking at, and if you want to show it to others, it's very hard to be on the same page. So we'll make it 2D, but without loss of generality. I mean, the ball can be anywhere, and what we'll visualize is the plane that slices through the ball and passes through the center screen like this. We're going to implement this visual explainer in its own HTML file. So let's create it here, explainer HTML. And similar as before, doc type, main tag, head. Let's call this pinhole camera model, because that's the technical term of what we're trying to figure out. And in the body, I'm just going to add a canvas. And let's open this file to test. We don't see much. The title is there only, and if we open the developer tools, the canvas is there too. Let's add it some style. Maybe a border is enough. Yeah, and I'm gonna make it the size of the page. So let's arrange this a little bit. I'm not going to use external files for this one because it's just prototyping something to figure out if we can do anything useful or not. And to access this in JavaScript, we're gonna have to give this an ID. And now we can begin our script tag here. Let's take the CTX from the canvas and the width and the height. I'm gonna extract these like so because they can be very useful. For example, when we draw our so-called pinhole, it's gonna be in the middle of the canvas, and I'm just going to use an arc at that location, and let's just make it a small 5 radius full circle like so. There it is. Now this is supposed to be a hole, and the only way light can get through inside a box there. So I'm just going to draw a horizontal line. Let me just make sure that we remember this part of the code does the pinhole, and that line is going to be our lens. From 0 to the width at the same height as the pinhole. Save. Refresh, and yeah. But maybe I don't want to emphasize it so much. Let's try to make it gray. And actually, if this is supposed to be a hole, maybe it's better if we draw it white so it really looks like a hole. In that way, later we can also draw things going through it and it's not going to block them. So it might make things more clear. So the pinhole, we make it white. And now maybe we can make this a little thicker because otherwise we don't see it so well. So let's give it 2 pixel line width. Save and refresh. Yeah, that's better, I think. And now the focal length, how far the sensor should be. Let's define this one up here. let's say 200. And the sensor is going to be defined using this. So same X as the pinhole. The Y depends on this focal length, and it's going to have a width, how large we want it to be. And here in the drawing area, maybe just above the lens, we're going to begin a path, move to the sensor X minus half the width, and we do the same thing line 2 with plus half the width, and we stroke. Okay, now I think the sensor is more important. We should emphasize it more. So I'm going to go here and say line width is equal to 4. I think that's much better. And it's time to draw our dissected ball, maybe somewhere here. So up, I'm going to define it ball as a point relative to this pinhole a bit to the left, and let's say a little more to the top, 20% of the height. And the radius, I'm just going to set it to 40. Now we draw it somewhere here at the bottom. I'm going to copy this pinhole because it's essentially another circle with these properties, and let's make it silver. And this is the ball. Save. Yeah. Now the next step is going to be tricky. I want to get these points on the side of the ball that are orthogonal to this direction here. And for that, we're going to use vectors. If you find vectors difficult or don't even know what they are, I have a video where we figured them out by coding. We'll visualize the vectors using arrows, which we draw using vectors. Kind of a chicken and egg thing. You'll see. And then make them move in some crazy ways to practice the operations. I will explain vectors in this video too, after we implement their basic functionality, so in about 3 minutes or so. But if they won't become clear after that, or you get confused at some point later in the video, I recommend you check that one out. We take things really slow over there. To calculate one of those points on the side of the ball, we're going to need to do several steps. First, get this delta pinhole minus the ball, and then normalize this delta vector, scale it by the radius of the ball, and then calculate the perpendicular direction and add it to the ball. And we're going to draw it basically same as we draw the pinhole. But with point X, point Y, and let's make it black. Now, this is not going to work before we implement our vector functions. And I'm going to do that in a separate file because it's also going to benefit our main project. So let's create vector.js by control-clicking it. And these functions are really simple to implement. Like adding is just adding each of those components and creating a new vector. Then subtracting, I'm just going to copy this, say here subtract, and this is a minus, and this is a minus. Scale has the first parameter a vector, but the second one just a scalar, so a simple number, and it's going to return the components multiplied by it, like so. The magnitude we can calculate using hypot, and we don't need to calculate any difference here because vectors are defined with their tip relative to 0, 0, so -0 does nothing. And then normalization. This sounds really fancy. It's just a way to make the vector have a length of 1, so we get its magnitude, and then we scale it by 1 divided by the magnitude. we wouldn't necessarily need this in our code here. Like, we could have scaled here directly with the ball radius divided by the original magnitude of that vector, but normalization really helps in taking things step by step. And last but not least, a way to calculate the perpendicular vector. We just returned the same thing, but flipped in this way. So now if we save and refresh, it works. But why it works, we can actually go through the steps one by one. I'll show you. Back in the explainer here, instead of showing the point at the end of this whole process, let's take delta, save and refresh, and we get this point right here. Now it's there because it's this delta between the pinhole and the ball center. We are just drawing it relative to the 0, 0 coordinate. Now, next step is to get the normalized form of this vector, and it's here. It's not at 0, 0, it's a length of 1 pixel away from it in that direction we had earlier, but it kind of looks like it's there. Then when we scale it by the ball radius, you can see that the original direction is preserved, and this magnitude here, this length, is the same as the ball radius. Now the next step, the perpendicular, makes the point disappear. That's because it's off screen there to the left. To make the next step a bit clearer, I'm actually gonna not do this perpendicular operation at the moment. Instead, I'm going to add here to the ball the previous scale vector and show the end result. So you see we got a point on the ball in this specific direction because we translated by the vector corresponding to the position of the ball. And now if we do add this perpendicular back in, you can see the point because it's not off screen anymore. It's relative to the center of the ball because it was translated as well. I hope this was clear. If not, please check that other video because it was made for those who haven't really seen vectors before. Now let's get also the point on the other side. For that, we can say here we want points on the side of the ball, and let's copy this with point A. Point B is the same, but we just subtract here, for example. You can also keep the addition and scale that perpendicular vector by -1 for another example. And here we can do this, save, refresh, and we have both those points. I would like to draw these kind of rays coming from here, going through the pinhole. Let's make them go to the pinhole first. So here I'm going to begin a path, move to the points X and Y, and line to the pinhole X and Y, and we stroke. Nice, but let's try to give this a different style. Let's make them black, same as these points here. Maybe a little bit thinner. Maybe we make them as dashed lines. Let's set the line dash to 2 pixels for the dash and 2 for the space. And I recommend we always clear the line dash after we do the drawing because it might affect other future drawings as well. This is okay. And to draw this all the way, we are going to use vector operations again. So let's define that ray as this difference, pinhole minus the point, and we should scale it to go outside the screen. But because the ball and the pinhole can have any kind of relationship to each other, it could be that the scaler you choose doesn't always make it go off the screen. So it's one of these times where normalizing gives you more control over it. So normalizing the ray gives us a ray with the unit length. And now maybe we decide on a magnitude or a length that is large enough, like the width of the screen is long enough to go off screen. And we can calculate an endpoint by adding the pinhole to a scaled, normalized vector. It's okay to write multiple operations on one line like that. So we take the endpoint, we put it here instead of the pinhole, save, and now it goes all the way there. And we see that the ball doesn't really appear on screen, not all of it. Part of it lands outside the sensor. We can also experiment a little bit and notice that if we make a smaller focal length, then it would fit. Or if we would keep the focal length the same as before, but increase the length of the sensor, it would also fit. I prefer this because it kind of looks like we are using much of the space. And thinking about different lengths, we can actually already see why different ones make the ball look smaller or larger. If we look in this triangle, we can even figure out the relationship between the focal length and the FOV. I'm sure it's gonna come in handy later. But now I don't really like these points visualized like that. I much rather had a line here showing like the diameter instead. So going here where we draw those points, I'm just going to remove it. And let's copy a line, maybe the one from this lens, and do it before this for each. So the first point is going to be point A, X, point A, Y. The second one, the same for point B, X, and Y. And let's make it black. Refresh, and that looks nice. And this is quite hard to draw on paper, really. You can try it. James did during the competition, but he also did some of these nice computer drawings as well. And we could try recreating those if we add more balls there. It's really quite easy. For example, here where we define the ball, we can say balls and prepare this to be an array instead of a single object. Let's arrange this a little bit. And I'm going to copy this like so and double these coordinates. So maybe 3 here and 4 here. And below, when we are drawing the ball and the points on the side of the ball, we just need to make this into balls. So now we loop through each of the balls like so. And all this code can go inside the for each. We just need to remember to close it as well. Save and refresh. And this looks quite similar to that. But for our explainer here with these distortions, I want the balls to be the same distance away from the focal length, just different angles. So I'm just going to put it in front here. Essentially removing this X offset, and this one, I think 25% if my math is right. Refresh, and yeah, this ball here looks smaller than this ball, even though they are the same size. That's because the sensor here is flat like that. If it would be a sphere, a hemisphere, let me show you. I just copy this pinhole here and let's call it hemisphere. It's the same as the pinhole, but the radius here is going to be the focal length. And I don't need that. I'm going to stroke with red and let's make it quite thick. Then, okay, we get the full circle, but that's okay. It shows that my math for making these on the same distance away from the center was correct. Half a circle here, or in 3D, a hemisphere. And now, if we look at these, they are the same size, And that's going to be the solution to our problem. Imagine bending the hemisphere like that. See how those distances look good now here on this plane? What we need to do for every point, let's focus on this one, is replace its current pixel value with the one from here. We need to figure out the formula for that. First thing we can do is measure this distance from the center. Let's call it d. Now imagine this distance d wrapped around the hemisphere. We need to find this angle. Let's call it theta. The full circumference here is 2 pi times the focal length. But we're only interested in a fraction of it. To get the angle in degrees, we'd multiply by 360. But for us, it's more useful to get them in radians, so we multiply by 2 pi. Now this d prime is the thing we really need. It tells us where the source pixel is, where we need to get the information from. In JavaScript, we can calculate the tangent of theta like so. And the tangent is also the opposite divided by the adjacent lengths. So to find d prime, we multiply by the focal length. To implement this in practice, we need to remember this is just a slice and the whole thing is 3D. But that part is straightforward, I think. We update to get d using these two side lengths. Then we pretty much have d prime already and can use it combined with this other angle phi to get the source pixel coordinates. All of these animations were made with a slightly more advanced version of the explainer. Your third homework is to try adding more features into yours and let's have a competition. Send me your versions and I'll demo my favorite around Christmas. For credits, I expect it to be at least interactive. Make it possible to move the ball with the mouse and change the focal length with the scroll wheel. Just those things make it already far more useful. You see, people like learning interactively like this. It's why apps like Brilliant are so popular. And if you like what they do and become good at this, maybe that's a career option to keep in mind. They seem to have openings. Let's go back to index.html and add a new section here before segmentation, distortion, where we use another canvas to visualize what effect it has. Now, this needs to have the same size as the input video. So we need to go to input.js and pretty much set it in a similar way as we do with this segmentation canvas. Distortion canvas. And there's a different one here for the simulation. Both of these need to match so we don't have surprises in the future. And duplicated code like this is a way to have more surprises in the future. Let's go to main.js, and what we'll need to do is get the distorted image data and pass it here to segment image instead. So everything then works with this distorted version. And this is the function we need to implement in image processing.js. Let's do it here at the bottom. Distort image given some image data. We take out the width, height, and data from that image data. The CTX, we take it from the distortion canvas, like so, and we start preparing the output data for debugging. Same width and height. And now we're going to loop through this, going through the pixel coordinates from 0 to the height and from 0 to the width, like so. We're going to need the center of the screen as a reference. So half the width and half the height. Actually, this doesn't depend on that, so let's move it at the top here. No reason to calculate it in each of those loops. And then dx and dy are going to be used to get this distance from the center point. So d is hypot of those differences. And then for theta, it's 2 pi times d divided by the circumference. It again doesn't depend on x or y, it's just depending on the focal length, which is necessary to be a parameter here. We'll worry about that later. But for now, let's go here and finalize our distortion correction function. So d prime, we take the tangent of theta multiplied by the focal length. Phi is the other angle that we're going to need to use when solving this 3D version of the problem. And then the source where we're going to take the pixel information from comes in this way, and we have to do it twice, once for x and once for y. Now, it's possible that we want to sample from somewhere that there is no information, so we should check if this is within an accepted range, like so. And if it is, let's get the index inside of this image data. So SRC index, we're going to have to round these values to avoid weird problems because indices are not floating point numbers, multiplied by the width plus SRCX rounded times 4 because of the RGBA components. And the target index is y times the width plus x multiplied by 4. Now all those RGBA components have to be modified, so I'm going to loop here through all these values and set the output data to target index plus I, coming from source index plus I. And at the end, when we have the output data, we just put it on the distortion canvas and return the output data. Now this will work when we pass a focal length, which we'll need to define in main.js after we read the image data, because it's going to need to be in pixels. And we will use a helper function for that, transforming the FOV from the parameters with the height of the image data. And then we can pass it here to distort image. Now let's save this and go to our math.js file to write these helper functions according to what we discovered earlier when playing with the explainer. And this other helper function to transform degrees to radians. And now let's save, refresh, simulate, and it's better than before. Remember, this is the one that used to be completely flipped. But it's still not perfect. What we've implemented here is the same as the azimuthal equidistant projection we see in maps. It's not a very common map projection, but it has applications, like if you study earthquakes or aviation. So practicing this means we just got a little better at understanding maps as well. Your fourth homework is to implement a way to better estimate the size of the balls using this projection. Instead, I'm going to show you another map projection, the Lambert azimuthal equal area projection. As the name says, it's an equal area projection. If we compare it with the previous one using Tissot's indicatrix of transformation, we see the areas of these ellipses doesn't change in this variant. There's still squishing happening because it's impossible to flatten a sphere without any of that, but that doesn't really matter to us. The code we have at the moment just needs those areas to be correct. So how hard can it be to implement? Bah, I like this visual more. These spheres or circles here are the key. You see, in this one, we don't bend the hemisphere. we draw a circle with this radius instead. The point lands in a slightly different place. And same as before, let's mark this distance d away from the center. It's the radius of that circle, so this is also d. Now inside the hemisphere, we notice this isosceles triangle here. Half of it is a right triangle, and this angle here is half of what we need for all that previous math to work. Now the sine of that angle is half d divided by the focal length. To get the angle itself, we use the inverse sine function, or the arcsine. But this is just half of theta, so we need to multiply it by 2 as well. So let's try this other formula here in image processing. Instead of this theta, we're gonna use this other theta. Refresh. And wow. Matching quite nicely. Let's try also the version where the simulator is looking at the centroid of those balls. Both of them work really well now. That rounding we did earlier is not the best thing we can do. It essentially snaps to the closest pixel and takes its value. But a better way would be to take all neighboring pixels into consideration. A method that does that in a clever way is called bilinear interpolation. It's also your 5th homework. Self-study it, explain it in a few paragraphs, and implement it here to get a better result. Now, if you play long enough with your explainer, you may realize this thing. We don't see those points on the diameter really. We see these other ones instead. So when we calculate our apparent radius, it's not half of the diameter of the sphere. It's of this circle here. And it changes quite a bit when the ball is really close. Maybe it matters. So let's try estimating the distance another way. The sine of this angle, let's call it alpha, is the true radius of the ball divided by that unknown distance. So to get that distance, we can just do this. The only problem, we don't know alpha, but we can get it from the other side. You see, we know the apparent radius of that circle from the area from before. And if we imagine it here, perpendicular to this gray radius, the tangent of alpha is that radius divided by the focal length. So inside of estimator.js, it seems like we can do this a different way now that we know the focal length. We get this alpha, arcsine, the apparent radii of I divided by the focal length, and then the distance becomes the ball's actual radius divided by sine of alpha. But we do need the focal length here. So we should pass it in main.js when we do estimate these distances. Save, refresh, and it doesn't work. And the reason for this is that we were sloppy earlier. I kind of made a mistake on purpose to show you the importance of cleaning up the code and things like that. So here, I don't know if you noticed, but after I removed that math pi, these are not the radii anymore. Sure, it worked before in this ratio because the pi's simplify, but they don't anymore, and we left this variable name called radius. So this can be a horrible source for confusion. Anyway, now it is a radius, so it can be like that. And if we save, refresh, it works. To tell if it works better than before or worse, we should zoom in here a little bit. So in the output, I'm going to scale this maybe 30. Refresh. And let's move this up. Maybe height, 10% of the height. Yeah, this is fine. So this is now the current version with the focal length. And let's see how it compares with the previous one. So in the estimator, I'm going to comment out these new calculations and revert the old ones. It does look like that red point is a bit on the upside. So yeah, we have a better version. And one advice I can give you now is remove the old version. So pretty much everyone who discovered something like this during the competition kept both of them and made it work with different parameter settings. That can be fine if the method really has something to add. And at this point, I believe it doesn't. Because even though this doesn't work with the focal length, we are using the focal length to account for the distortion problem. And if we do remove it, the previous version that is, we can notice some other things as well, like that these initial apparent radii are not needed. Or even if we go to the parameters, that these initial distances to the balls are not needed either. So the overall code becomes simpler, and in my opinion, the other version didn't have anything to add really. Now, one thing caught my eye here. Sine of arc sine of something is useless because they cancel out. So we can just take this here, remove this line, and this is more efficient because those are expensive computations. So save, restart. Nice. Seems to work just as before. The change here is not very visible. So implementing a way to score this result starts to feel important. Your sixth homework is that you can choose to either measure how far these predictions are from what the simulator says, or implement a way to measure how round this shape is. The second one is better, I think, because we can use it on the results from the video as well. I've shown you how you can measure roundness at least twice. In the machine learning course, where it helped us tell clocks apart from other drawings, and in that portal opening game tutorial inspired by Doctor Strange. Now, recently I've watched this video from 3Blue1Brown where Grant interviews Terence Tao. It's a really nice watch teaching how the ancients figured out many things about the cosmos. I hope you'll watch it and realize how similar the math we did here is to what they did thousands of years ago, and that you're also understanding some cosmology now because of it. Now, before we move on to the next important step, I want to go back to image processing and just show you as an example how different this code could look like if we rearrange things, if we try to simplify things or use the vector operations since we have them already. This is important to realize because sometimes what you understand from the problem is not what the code shows. And I think it's a great practice. See, for example, here in the previous version with this theta, we had 2 pi d divided by the circumference. But there's a 2 pi times the focal length there. So basically, this is just d divided by the focal length, and it should still work as before. See how you don't understand why this relationship is here, even though the previous one with the circumference made sense? This is something to look out for. People may figure out the math or simplify it in a way that becomes unfamiliar, and you should be able to trace if it's correct or not. And more things here. So If we would write these with vectors, this math could look different as well. This dx and dy, it's essentially a delta subtracting xy minus the center. So we don't need these dx and dy. Just make sure here that we say delta x, delta y, and here delta y, delta x. Now, this doesn't work because we don't have our vector file imported here. So let's do that, vector.js. And if we save and refresh, same as before. But this can still look much more different. See, this d here is essentially the magnitude of delta. So magnitude of delta, and this phi is the direction of delta. We don't have that function implemented yet, but it's what usually would go inside one of these vector files. So the direction is defined in this way. Now there's more. Here, this src x and y, it kind of looks again like doing the same thing, but just a little bit different. Sine and cosine of phi, this seems to be the x and y components of the normalized delta, which is scaled by d prime and added to center x. So really what we have here is the src adding center to scale normalized delta d prime. And we can replace these src x here, here, and here with src.x and src y here, here, and here with src.y. And we also noticed this phi was not needed, even though it was used and felt important previously. And this code does look now quite unfamiliar from what we had previously, but it works the same. If we save, refresh, exactly the same outcome. So now the question is, how does all our effort look in the original video? Well, the distortion appears here, this correction, and the circle. Yeah, I think there's already a clear improvement. To understand how tilting the pen affects what the camera sees, we can update the simulation to make it more complete. Once we do that, things will become more complicated. And that's when I'll really teach you how to break the problem into smaller parts, so they're manageable. It might be a good idea to be well rested then, so I recommend you plan for a break after we update this simulation. Let's go to our simulator and model now the camera pen inside it as well. We'll do that starting with the stick. So let's go somewhere here after the balls and say stick geometry is a new box geometry with one width, pen height, and one depth. And the material, I'm just going to initialize a new basic material. This is going to default to white. The stick itself is going to be a mesh with this geometry and this material. And let's add it to the scene. Now I want this stick to be the thing that is moving here. So instead of changing the camera position, we are going to say stick position is like that. And the camera is going to be a static camera. So let's rename this to static camera. And I'm going to fix its position relative to this initial position. I'm just going to move it further back so we can see what the stick is doing. And we don't need to change its look at either because it's already looking in that direction. Now save, refresh, and we can see that stick and the balls very far away over there. Maybe we can move a little closer. Say 80. Yeah, better. And now this stick is moving according to the camera position. I would like to focus on its tip instead, the thing that is drawing. So let's go to the parameters and define the tip initial position. It's going to be same as the camera, but 0 instead of pen height. And in the simulator, we can use it here when generating the path for our pen. So here, tip. And now save, refresh. And the pen did move to that, but it's the middle of this stick that is following that path. And we want it to be its bottom tip. Now, this can get messy, especially because we're going to add a camera on top of that stick and rotate it in crazy ways. It's much easier if we use a group and add these things into it and offset everything inside that group to their respective place. I'll show you. So above this stick, we're going to define the camera pen as a group. And after we have the stick here, we're going to add it to the camera pen group. And now to the scene, we just add the entire group. We also have to remember to move here the camera pen as a whole. Now, if you save this and refresh, we're going to get exactly the same as before. But now we can offset this stick Y value, the position Y, to half the pen height. And when we save and refresh, you can see now this follows perfectly that path, and this where the camera is perfectly centered with this viewing plane that we have here. So it's good. I'm gonna draw the camera on the top as a kind of box. So let's make it more realistic like that. I just chose these properties because they look good, and similarly the mesh, I'm using the same material as we had defined earlier. The position is going to be pen height this time, and let's add this to the group as well. Save, refresh, and there you have it. Now we're gonna add the real camera in this group as well. So for that, I'm going to copy here this static camera, and let's move this aspect ratio above it because it's going to use the same. And this is going to be the camera that moves with the pen. So its position is going to be the same as this box we defined earlier at pen height Y, and let's add it into the group. Now it will look the same if we refresh, but if we change here this static camera in the renderer so that it uses the new camera we defined, save, refresh. Now it looks same as before with the camera facing at that wall. And our system here started working again. Now it could be useful to switch between this camera and the static camera from time to time to understand things better. So let's use this useStaticCamera variable to tell us whether we use the static camera or this camera. And I'm going to define it all the way here at the top. So let's say static camera is true. And when this is true, we will get this view, which, by the way, doesn't work here because the balls appear so far away that our point is probably somewhere back. And when this is false, we get this more familiar view. Now, one thing we should still remember to do is here, this is not the true camera position anymore, it's the tip position. So let's rename it. And the whole reason for modeling that pen like that is so we can change its rotation properties. So here, when we generate the circle path, we can also tell it how to tilt. And for that, a way of calling these angles are the pitch. So if you think about airplanes, it's how the airplane moves up or down like that. And the yaw is how the plane would turn like that. And then the roll, let's set this one to something different. It's when the plane rolls like that. I don't know if it's easy for you to remember this plane movements analogy, but it works for me, so try it out. And we'll pass these next to these other properties. And for them to affect our pen, we have to go here after we change its position. We can also destructure to take out the pitch, yaw, and roll from this pen position and set the rotation to those values like so. Now I think this should be called maybe tip properties or tip info, something like that. Anyway, if you save and refresh, now these look at an angle. The true tip should be here, but the camera appears to be to the left because it is. So if we're going to set this one to true just to debug, you're going to see that the camera is a little bit to the left from this tip right here. So probably our position estimation is correct. Let's make sure it is. Here, where we are rendering, after we render, we can ask Three.js to tell us the camera position in the world coordinates. We prepare a vector for that, and then we tell the camera to get the world position and put them inside of this vector. So now here we can return the tip properties and the camera position. That means we're gonna have to change some things, like going to input here, where the simulation gives us this is no longer the true camera position. So let's rename this to something like metadata, save. And now in main.js, this is the metadata. And in the output where we visualize things, we also have to change this draw output function. This becomes metadata here. And if there is metadata, because the videos don't have it, let's take out the X and Z from the metadata camera position to see if our camera estimate is correct. And we don't need this here anymore, and we can make it simpler. Now save, refresh, and look at that. Our estimate seems to be aligning quite well with this red dot. And now everything looks a little bit off center, but that's okay. We're confident that we can move on to estimate the tip position. So let's put here tip properties like so. And now back in the simulator, we are putting a different value for this roll, but to really account for all kind of changes, we're gonna do something crazy. What Bas did during the competition. I'm going to randomize these values, like maybe between -0.1 and 0.1. Let's implement this function in the math. So a function for getting random values inside an interval between min and max. Math.random gives a value between 0 and 1. So let's scale this by the difference and add now this min as an offset. And when we save and refresh, we see now this kind of shaky movement. And Bas used it for all of the angles. So it was crazy like this. Yeah, it's gonna be interesting if we can solve this one out. I don't know if you noticed, but in some of the frames, the balls were cut, and I think that's a little bit too much. So we can use smaller angles there. Buzz called these disturbances, so let's set this to maybe 0.05. I mean, if in the original video that I recorded, the balls were always on the screen, it's very likely enough for us to work with a lower value there. Yeah, this seems challenging and the balls look on the screen all the time. And now we can go back to main.js, and after we have the camera position, we can start to think how to get the tip position starting from this camera position and whatever we can infer from those images. Let's set it first to the camera position, so we have it as a starting point, and then think how to modify these values in some way. Now I'm just going to replace everywhere the camera position and these camera positions from here. Let's rename it to tip positions because we change our focus from the camera to the tip, and everything should still work as before. Making progress now is not easy. We need to estimate the rotation of the camera from the image somehow. Then we need to apply it correctly to locate the tip. But now we're even lacking the Y position of the camera. It needs to be there for all the others to work. None of these are trivial, and at first sight it seems like we need all of them implemented before we can test again. This is where small bugs are inevitable unless we find a way to implement and test those independently. Maybe you figured out by now, the trick is to use all the information in that metadata. The simulator has the answers to these two. It knows what the angles are and where the camera is, so we can jump directly into step 3 if we wanted. And if we work in a team, this is where we could delegate tasks. Some try to detect the angles from the image and get as close to these values as possible. Others can focus on the camera Y value instead. And meanwhile, we are not stuck waiting for them. I hope you see how valuable this simulation is by now. Let's use now the simulation to get a hold of those true angles, like so. I'm taking them from the metadata tip properties. And I'm marking this as a part of the code that we need to figure out how to do it without the metadata. But now with this help, we can think how they can be applied here. And we can actually take this a step further. Like, why solve this difficult problem with all of these random all at once when we can start with these ones 0, and now the only thing that changes is the pitch. So the disturbance seems to only be vertical like this here on the z-axis. That tells us that we have to do something to this value. And even if you're not that good at math, you can probably guess that that pen, when we know the camera position and we want the tip can move on the surface of a sphere. So something to do with that circle trigonometry again. And because now we isolated such a small problem, you might be able to solve it using guess and check. So for example, let's try to add here the pen height multiplied by the sine of the pitch. It's the first thing that comes to my mind. And I think we made the problem worse. Maybe we should put a minus here instead. And look at that, we solved this. It looks perfectly aligned. Now we only solved it because of this approach, like taking the big problem, making it smaller, taking the smaller problem, making it even smaller, and now we only solved a fraction of the big one. But it shows that you don't have to know the complete solution to everything. And when the problem is this small, you can approach it also using this guess and check approach. I don't recommend it, and I will show you later how to rotate things properly in 3D. I will explain that. But now I just want to show how effective this technique can be. Like in the simulator, let's activate now the roll as well. So now we get this that we have to fix. And very likely it's going to be something similar. So let's try again the same, but using the roll. Maybe we're lucky. And first try. Now, for this y value, we have a problem because we don't have one to start with. Like if you log here the tip position y, which is the same as the camera position y, I'll remind you that we don't have it because when we estimated the camera position, we just used the 2D approach. So there is no y. But we can get a y from the simulator in the same way. So here we can say the camera position y, let's just set it to be the one from the camera position in the metadata. And now we do have one to start from. And it looks okay. The pen height is 18, but because of the small tilts and the tip always touching the table, the camera is naturally going to go a little bit lower than that. And we should get here 0. And it depends on the roll and the pitch in some way. So first guess, pen height times, let's use the cosine now, because this should be a big difference. If the sine made the small difference before, now we need the big one because we have to move all the way down. So out of phase. And we messed up again. But probably it means that putting a minus here. Yeah, we get 0. This value is just really, really close to 0, and it's a floating point artifact. Now notice here we don't use the yaw at all. And actually, if we go back to the simulator and make these random values appear to the yaw, they don't bother us at all. That's because our camera distortion fix handled those issues. And rotating the pen like that doesn't have any effect on the tip's final position. It's important to be able to analyze things like this and know what you really need and what not when solving a problem. Now we have 2 big ones, essentially, and let's begin with this first one. But to make things more clear in the explanation, I'm going to go to the simulator and remove these disturbances for now. And now we don't get dizzy when looking at this image. The goal now is to find the camera Y location, so it doesn't matter if it's rotated in some way, the Y doesn't change. To figure out the camera Y coordinate, we need to start using the red ball. This will be your 7th homework. You can either update homework 2 or improve James's geometric approach we already have implemented. I won't be doing any of those because I want to teach you about local search. It's a powerful and really general way to solve problems like this, and I think it's even simpler than those other ones. To understand how it works, we have to think in a different way. Can you tell how good this solution candidate is? I mean, the best one is at the intersection, but how good is this? Can you compare it, say, to this other one? Or this? Can you sort these somehow? We can measure that goodness as the distance to this surface plus the distance to this other one. We can say this candidate has a lower error or a higher score. Sometimes that makes more sense. Let's implement these error functions next. In Math.js, let's begin by implementing an error function that tells how far we are from the surface of a sphere. So we are at this point, how far are we from the sphere centered at this center and this radius? And for that, we can just return the distance between the point and the center and minus the radius. Now this will work if our points are outside of the sphere, but we can also be inside it. So that's also a kind of error. And we can put this absolute value in front so that we don't get negative errors. There's no such thing. And using this function, we can define a more complicated function. That is the error, how far are we from the surface of two spheres. I'm just gonna add up the error from being on one sphere plus the error from being on the other. Computers are very powerful things. They can do many calculations really quickly. Your 8th homework is to implement the guess and check approach. Try many random candidates, calculate their error, and return the best one. Instead, I'll show you how to display those errors on a grid. Let's go to this output.js, and after we scale here, let's draw a grid. We're gonna need to implement this function, taking ctx as a parameter. It's going to draw a grid over the canvas. So let's loop over the z values. I'm going on both sides of the origin. And same for the x value. And now let's stroke a rectangle centered at this x and z with a width and height of 1. So it's a square. And I think that our line width is very thick. If we don't set it to something smaller like this, let's also make the lines gray so the grid is not so dominant. Now save, refresh, and you can see it appearing here. But I would like to move the balls in the center screen so that we see it symmetric. So let's just put this as it was once before, and I'm gonna zoom out a bit, so maybe 15 for now. Save and refresh, and let's make it bigger. I think we can double it like this, maybe 4 times the other way. So 40, 40, 20, 20. That looks about right. And now we're going to color these cells according to the error from each of those points to the surface of these spheres indicated by the circles we have here growing and shrinking. So we need to tell the grid here also where these balls are. The center points are the only things needed, and the distances to the balls as well. These are going to be the centers and the radii of those spheres. So let me take them out so it's clear, like in our math functions from earlier. Radii of 1 and radii of 2. And now inside this loop, we are going to define the point. It's going to be at x. Now for the y, I'm just going to set 0 for now. And z we get from the grid here. The error is going to be error to spheres, point, C1, R1, C2, R2. And the fill style, I'm just going to define an RGB color with the error, error, and error for each of these values. So it's a gray value, really, and if the error is small, it's going to be black. If the error is high, it's going to be closer to white. And with this fill style, we can fill, rect, save, refresh, and our grid looks pretty black. But when these spheres are big like that, I can kind of see a lighter gray in the middle. And then when they shrink, this middle part becomes darker and darker, almost black. So let's increase this intensity a little bit. I'm just going to multiply the error, let's say by 10, and pass this intensity value here. And now you can see this much clearer. And you can see some patterns in the grid as well. It kind of looks like these circles that we are drawing here. Let's make the intensity even larger and see if it's better. Yeah, I can clearly tell these shapes are there. But they don't align perfectly. And the reason for that is that those circles were drawn relative to the y coordinate of these green and blue balls. So let's replace here using one of them, let's say c1.y, save, refresh. And now these align with those circles perfectly. Actually, we don't need those circles there anymore. It just adds unnecessary things. So I'm going to comment them out for now. Now this can be a bit slow because we are drawing this large grid here. And if it doesn't work for you very well, you can try a different grid size. But I'm going to continue like this. Now, local search works like this. Imagine the grid is like some stairs that go in all directions. We start somewhere and just look around in the local neighborhood and decide which way to go to reach the bottom as fast as possible. Doing this again and again many times, we will reach the bottom. People also call this hill climbing. It makes more sense if you flip the error around and compute a score instead. Then you'd want to go upstairs towards the top. To implement the local search variant of the position estimator, we're going to go in estimator.js and I'm going to rename this as estimate camera position underscore James, just to still have a reference to it if needed, and implement the one that is actually used by the program from scratch. Given these distances to the balls and also the real ball information itself, so I'm going to take out here some constants with these values because it matches the functions we made earlier and I think it makes things more clear. Now the starting point where we are in the beginning can be anywhere. Let's just say start point is x is 3, z is 10. And y, I'm going to fix it for now to be c1.y. So we are at the same level as those bottom two balls. And point is equal to the starting point. And let's say the error that we tried to minimize, I'm going to set it to a huge value in the beginning. So as soon as we find a smaller one, it's going to get replaced. And now we loop. We try to do 300 steps. And in each step, I'm going to try to go first to the left. Let's get a point for left by decreasing the x. And let's try for the right as well with R here and the plus. And then let's try forward. If we think about that z direction, it's -1 here. And backwards, let's say b +1. Now for each of these we have to calculate an error and I don't want to repeat many lines of code, so I'm just going to add these into an array of candidates and now we can use a for each. So for each candidate we are going to calculate the error from that position to the surface of the sphere defined by those properties, and then if this error is smaller than the best one we had so far, we are going to update that minimum error to this new minimum and update the point to be this candidate. And at the bottom here, we return the point. And now if we save and refresh, you can see points appearing here, not really on a circle, but kind of a circular path. They just all align with these grid cells because our step here for changing the values is 1, so it matches with the cells. But we could use a smaller step as well. Let's say we want to use 0.1 instead. So I'm going to replace here everywhere step with this. Save, refresh, and just look at how nice these points are becoming here. Really great. We can do this because the grid isn't really there. The surface is smooth, like this. You can play with it in Desmos. I've seen people explain like with a ball going downhill to reach the bottom, but I don't like that because the ball would have momentum. So it might do weird things here. Maybe if you cover the surface with honey or something, it's better, but we're really just doing small steps. And just look at how nice these points are becoming here. Really great. What's this? What's happening here? Can you figure out what the problem is? Let me know in the comments if you do. I'm going to show you what the problem is by visualizing the path we take to reach that point. So let's call this the optimization path and start it at the start point. And now every time we get a new point, so here I'm going to add it to this optimization path, push point, and we return here not just this point, but also the optimization path. So that means we have to do a little bit changes. In main here, when we estimate the camera position, we get two things. We get a point. So let's say we refer to this point as camera position. So this code still works. And now here we also get this optimization path. Let's also align this so I can still read what this function says on screen without scrolling horizontally. And pass this optimization path to visualize it in this draw output function. We pass it here as the last parameter. And I'm going to visualize it next to this other path before it, let's say, optimization path in orange. Save and refresh. And starting at that random point, we go along this path until our solution, where those spheres intersect. Except for here, because we've reached the end of the path, so to speak. We have a limited number of steps here, and they are just too few in this case. So changing the step size to a smaller one means we have to do more steps to reach that. Like if we put 1,000 here, we should get the proper circle in the end. Let's see. Yeah, looks like no problems this time. Now, setting this number of iterations can be tricky sometimes because now it seems to depend on that. But it's also possible to avoid using it. Like we can comment out this for loop and replace it with a while loop instead. We just look for improvements. When they stop happening, then we can stop the loop. So for example, we can say improved is equal to true, then begin a while loop while it has improved. Let's set it to false. And if this happens here, we can reset it to true. So the loop only goes as far as we found improvements. Save and refresh to see pretty much the same result as before. We just don't need that number of iterations anymore. It's going to stop when it can't find any better. What I also want to show you is that we can really start at any starting point. Like let's put here random value between -10 +10 and the z, let's say between 10 and 30. Save, refresh, And look at that. Anywhere this orange path starts, it ends up in this correct place. Almost anywhere, because there's a reason why I put here these positive values. If we have negative values here, like -30, we may start our search on the other side, so then it converges to this other circle intersection there. And we're getting now this mirror reflected circles here, but we only care about these ones. So that's why we can start anywhere on this side and we should be okay. Now we're gonna undo here a little bit because I want to bring back those iterations. I want to show you something different. So let's undo until that for loop comes up again. Now, what I want to show is that randomness also works here when finding a candidate. But because we're going to decide it randomly, sometimes we'll make a wrong choice. So then I don't want to stop that while loop we had previously too early. I want to control the number of iterations again. And here I'm going to remove all of this thing and just define here candidate is equal to, and the x goes around point x, a random value between minus and plus this max step this time. So let's rename this variable name to mean the new thing it means. Same thing for the z. And I want you to note that doing this means that we don't have to think what do those candidates mean, like before we had left, right, forward, backwards. In 3 dimensions, maybe you can still use up and down, but what then? This local search works in any number of dimensions. It's a very general, powerful technique. So yeah, there is value to this approach. And the y, I'm just going to set it to point y because I don't want it to change. And no need for this for each anymore. I'm just going to use the candidate directly there, save, and let's see what we get. You can see this path is quite random now, but seems to still converge on that circle mostly. When the path is too long, it doesn't work well because too much randomness added up here doesn't have enough time to converge in the given number of iterations. But it's also because the step that we are using now is really small. I mean, this is a max step now. Before we used it as an actual step. So maybe we increase this and see if we get better results. Now you can see bigger steps, so these jumps in the path are bigger, and looks like we are ending up on this circle pretty much. It's very similar to what we had previously, but it's crazy that just doing random jumps is still working quite well. There's one thing I still want to show you in Desmos. If we move these circles so they don't intersect, you'll see the error is the same everywhere here. Now, this can happen even with our balls, if, for example, one obscures the other. I was just nice and didn't let that happen when recording the videos. But what would you do in that case? What's the answer? My intuition says it should be somewhere in the middle, but from this there's no way to decide really, and our algorithm is just gonna stop at the corner here. The trick is to add an exponent, raising to the second power. This curves the whole surface and gives a clear answer here. People do this for another reason as well. You see, now these functions are differentiable. You can take the partial derivatives and use those to know in which direction to go. This is more efficient because you don't need to search in the neighborhood. Your 9th homework is to implement gradient descent and see it working in practice. Experiment with different learning rates and describe what you notice in a few paragraphs. So even with this randomness, this technique is still quite powerful really. And let me show you just how general it is. Because now we're gonna change to actually find the y location. Let's start at a random place, let's say 1, and we need to introduce the third sphere. So here at the top, I'm going to say C0 is the center of the ball at 0, and then R0 is the distances to the balls of 0. We're gonna need to modify the Y values as well, so these also change. And the error for 2 spheres has to change to an error for 3 spheres. And let's add these 2 new parameters here as well. And that's it. We just need to implement this extra function in math.js. And that's really straightforward. We basically just add the error to 1 sphere 3 times. Much simpler than doing the mathematics I asked you in that one homework. I can even call this one for 1 sphere here and then add the error for 2 spheres, which is a little shorter way to write this. Of course, writing these functions a little bit different way, you can even loop 3 times that one function. And now save, refresh. And look at that. It's not as good as before, because now that path, even though it looks 2D, it goes in 3D as well. So it has more chance of making mistakes, so to speak. And we're gonna need more iterations. Let's go back to this estimator and define the iterations here at the top. I'm going to say it's a parameter, but let's set it to 10,000 and replace this here. Save and refresh. And it's significantly slower now, but not really because of the number of iterations. I'll show you. If we do want to reduce the number of iterations, one trick we can do is not start here every time, because the previous position that we found is more likely to be close to the new one when the camera moves just a little bit. So if you want to reduce this number of iterations, you could take out this start point here. Well, let's use let, because it's going to change. I'm going to change it here after this for loop and set it to the point we just found. And now the technique is going to work well even with fewer iterations, let's say 1,000. Because essentially what it does is it's fine-tuning in this very small neighborhood there. It doesn't need to go all the way from the beginning, so the end result looks quite good with fewer iterations. But I want to use more iterations because it's going to give a much better result. And also because I want to show you that those iterations themselves are not the reason for this slowness. The reason is we are drawing here 10,000 different orange circles there. So if we disable this optimization path and even the grid, because we only draw it there to understand what's going on. For our estimator, there is no grid. And now if we save and refresh, you're gonna see this going really fast, because 10,000 steps there is nothing really for a computer. Don't get me wrong, if you do solve this in an analytical way, then you will get a much faster solution. But that's besides the point. Think how hard it is to account for another ball, like let's say there's another one going in as an input. In this approach, we just add it here, but this is really to make things clear. You could pass this information directly to this error function, and that error function could be written as a loop. So if more satellites appear from time to time, this function knows what to do and use all of them to get as accurate of a result as possible. That's really the powerful thing in this approach. It's very flexible. And sometimes the number of dimensions here is not just 3, it can go higher. The intuition kind of breaks in 3D already, but I like to think of it like this. Imagine you are a fish in some cold water. It's dark, so you don't see anything, but you can feel in which way is warmer. So you swim in that direction, turning as needed until you find the warmest place. And because it's dark, I can imagine it in higher dimensions as well. I don't need to understand how those dimensions work, just that hyperfish can move in any of them. If you've taken my self-driving car course, you've seen local search working in higher dimensions. There we optimized all those weights and biases, so many dimensions. Now, there I called this a mutation, and the overall optimization a genetic algorithm. It's because we were playing around with how much we mutate, and were selectively choosing which car is the best. We were part of the algorithm, guiding it to do a kind of natural selection. Anyway, local search wasn't enough there because that space had a lot of local optima, places where the water is warmer than the surroundings. If you start in the random place, it's unlikely you'll reach the warmest place in the lake. So to find the perfect car brain, we had to jump around, and genetic algorithms are one way to do that. There are other optimization algorithms as well. Many of them are based on this local search, so I really hope you understand it well. I've also used local search to explain why circles enclose the largest area, or in my live streams when coding the strandbest. Each of those lengths had to be optimized so the path is flat at the bottom and somewhat triangular otherwise. Theo Jansen, the artist who invented the strandbest, used the genetic algorithm when designing them. Do you see how different these examples can be and how generally useful these techniques are? It's even an active area of research. My former student and colleague, Lahare, researched local search to see how it can solve the TSP. It's a problem where we need to find the best way to visit a list of places. A really hard problem when there are many places to visit. And Pasi, who was our PhD supervisor back then, is an expert on clustering, a type of machine learning. The first algorithm he teaches is k-means. Many other algorithms are based on it, and k-means is also a local search.
With centroids initialized randomly, each of them takes small steps until they converge to a good place. It may not be the best place. That's why better algorithms like random swap are still being invented.
I could go on all day giving examples like this. James even used the genetic algorithm during the competition to estimate my camera lens properties. You can find optimization problems everywhere. Now with this method, we are getting a y value as well. So let's go back to main.js. And if we remove this from here, save, refresh, you can see that the values we get printed here for the tip are really close to 0. They are not 0 because there is some error in our estimate, but seems like the problem is solved pretty much. We can remove this log from here. And what we're left with is this last one. Now let's focus on figuring out these angles from the image itself. First thought that comes to mind is to measure this angle here to get the roll, and how up or down the balls appear gives us the pitch. This, or something along these lines, was a very common approach during the competition, so you can learn more by studying those entries, and I'm giving it to you as a homework. Your 10th homework is to measure the roll from the image in this way. Update the code with the value you estimated and compare to what the simulator gives. Describe what you observe in a few paragraphs.
The problem with this is that that angle depends also on the camera position.
Like here, the pen is straight, there is no roll. But this angle here is not 0 because of perspective. Because of that, I'll teach you a different approach instead. What we'll do is measure the 3D rotation vector to each ball in 2 ways. First, from what the camera sees, and then from the estimated camera position and ball coordinates. It's what the camera would see if not rotated. Then what we'll do is calculate the amount needed to rotate so the observed directions match the target ones. Those would undo the rotation. The pitch and yaw are enough for this one ball. But we have 3 targets, so we need to rotate like this as well. Now, the yaw wasn't important before, but in this approach, we'll need to measure how well those directions align. And without the yaw, they often wouldn't. Let's begin by measuring the directions the camera sees and visualizing them to make sure they are as expected. We're going to use a new canvas for that. Maybe I copied this distortion part here, and let's just say directions, and this is going to be the directions canvas. It will be a 3D scene, and let me just make it the same as our simulation canvas. We'll implement this in a separate file here at some point after we include 3JS. And now Control-click to create this file. And this part I don't really like. We're gonna use underscore to define some constants and variables because they otherwise conflict with the ones we defined in the simulator. Normally I'd be completely against this, but this viewer is something that we won't really need at the end. We can just remove it. So I'm not going to redesign the whole code just to avoid a small thing like this. So keep in mind underscore for everything in this file, pretty much. So this is going to be a new WebGL renderer on this directions canvas. And let's set the anti-aliasing to true. Save. And let's test just to make sure that this canvas initializes properly, and it does. Now the scene. And inside of the scene, we are going to define some arrows. And the way we'll do that is like this. I want 3 different arrows, red, green, and blue, for the different directions. So a quick way to do it is an array with a 1, 0, 0, and then the color red, then a 0, 1, 0, and the color green, and 0, 0, 1, and the color blue. And for each of these, we're going to remap them. So we take this whole group, components, X, Y, Z, and color, let's call them that, and we generate a new arrow helper using functions from 3JS. The arrow points at this XYZ and starts at XYZ equal to 0. I'm going to use the length of 1 for these arrows, so they're going to be small, they're in the center, and let's pass the color. Now for each of these arrows, we are going to take them and add them to this scene. To view the scene, we'll need the camera as well, and the aspect ratio that we're going to use is the one coming from this directions canvas, width divided by the height. And now the camera is going to be a perspective camera. I'm using the same FOV as all the other cameras and this aspect ratio. And now for the position, I'm just going to offset the Z a little bit so that we see the arrows from behind. And let's render the scene from this camera. Save, refresh, and you can see these arrows here. Now I want to be able to update them to show any directions. So for that, a function like update directions viewer given some directions is going to be very helpful. We're going to loop through all these arrows one by one and set the direction according to the respective direction given in the parameter. And to test if this works, we're going to maybe go here and define some random vectors. We're going to generate them using the array class. So I need 3 of them, and the callback function here is going to say what each vector is going to look like. x component, random between -1 and 1. And let's do the same for y and z. And with these random vectors, we can update the directions viewer. And we should remember to render the scene every time we update the directions viewer like this. So save, refresh, and here are some random directions, and others, and others. Seems like it works. Now, to figure out the directions of each of these as we see them from the camera, we need to first find their center points. So let's do that in the segment image function. We are going to do it by first accumulating all the coordinates of the red, green, and blue pixels and then averaging them. So R's, greens, blues, reds, greens, and blues are going to be stored in this. And here we are going to have to figure out the x and y from this pixel index, which is I divided by 4. Let's be clear about it. P index I divided by 4. And then x is P index modulo width. And the y is P index divided by width. But let's remember the floor there as well. And here, if the new red value is not 0, then I'm using that syntax from earlier and just adding this xy location to the R's array. And we do the same thing with the green and the blue, with the green and the blue. And using these R's, greens, and blues, we're going to calculate those centroids. So I'm going to do that in an array like this, where I just average the points inside of the R's, and then same for the greens and the blues. We're going to have to implement this average points function, but to debug, we can quickly say now for each centroid, take their x and y and draw a circle on CTX with xy, let's say a radius of 5, and let's make it white. Now, just a quick thing before implementing that function, these RGB counts now are calculated in a way that can be done faster using these new vectors. We can take it out from here and from here. And when we have those values, we can just say RGB counts is an array with the length of the first one and the second and the third. No point to have overcomplicated code when things can be done easier. Now save, and in the math.js file, we are going to implement this new function to average points. So given some points, we start off with the average at 0, and first we calculate the sum. So going through all of the points one by one, I take out their x and y value and add to this average x and to the average y. And then when we're done with this, we can just divide each of them by how many points we have. And return this average. Save, refresh, and if you scroll down, you're going to see these center points. And to calculate the directions, imagine this is a screen in front of you and you are a focal length away from it. So we are going to need the focal length inside of this segment image, like so. And to get the direction vectors, it's useful to first have access to the screen center point. So half the width, half the height. And then I'm going to remap these centroids one by one, taking the x and y component from them and creating a new 3D vector using it. So the x component of this 3D vector is x minus the center x. The y should be I minus the center y. And the z is minus the focal length, because it's in front of us. Now, when talking about directions, direction vectors, it's typical that they are normalized. you don't take the magnitude into account. And we don't have a function for this. We're gonna have to implement it. But first, let's remember here to return also these directions. And now we can close this and index HTML. And inside of main.js, the segment image function now will also return these directions, but only if we pass the focal length as an additional parameter. And we can visualize these directions, maybe here where we draw the other output. But this only works if we go to our vector file and implement the 3D normalization function. Now, if you look at different libraries and how they handle this, some might combine 2D vectors and 3D vectors in one place. Some might have different objects for 2 and 3D vectors. In this case, I'm just going to separate them like this. So we have a normalize, assuming that's the 2D version, and for 3D, we put 3D at the end of everything. And if we save and refresh, we see now the directions updating there, barely, because we're quite far from them now since they're pointing the other direction. So let's try to get closer in the directions viewer, maybe 0.1 here, save and refresh. And that's better, but it's upside down. So here where we are calculating the y, we forget to account that y in the 2D image space goes downwards, and in our 3D environment it goes the other way around. So save, refresh, and now it's like that. But I don't really like 3D very much. I try to make myself realize that those are going in that direction, but sometimes I see them pointing towards me instead, and it's very confusing. We could try closing this and maybe going a little bit upwards with the camera. Let's say 0.05. A little better. Usually playing with these values, maybe rotating a bit as well, like on the X. Okay, this is maybe a little bit more convincing, to me at least, that they are going that way. Up to you. If it worked for you in the first one, just go with it. The idea is to make things clear what's going on. And now that we have these directions that the camera sees, let's reintroduce those disturbances. So in the simulator, go down here where we are generating the circle path, and let's re-add them. 0.05 was a good value. And now we see them also going like that. But we can calculate the target directions, the ones that we want to calculate the difference to, by just using the camera estimated position and the real coordinates of the balls. I'll show you. Close this, and in main.js, maybe here after we get the camera position, we're going to define these target directions by remapping the balls. Each ball we normalize because they're going to be directions, and we take ball minus the camera position basically to get the arrows pointing at the balls. Now these I want to visualize alongside the others in this directions viewer. So it's going to be a second parameter, and let's save this. We're going to need to update the directions viewer and also implement this subtract 3D function. That's easy. Going to the vector again, and I'm going to copy the subtract 2D function here at the bottom in the 3D section and add there a 3D and the Z component. Close this, and in the direction viewer I'm going to get a new set of arrows. So let's copy this. like so. And these are going to be our target arrows. So let's rename it like so. And remember to copy this one here too. They're going to be pretty much the same as these ones in the beginning, but I'm going to use a darker tint of each of the colors to tell them apart. And at the bottom, for this update directions viewer, we need the second parameter. And this call we had here, it's something we forgot to remove. It was the early debugging with random vectors in the beginning. To update the target arrows with these target directions, we just copy this line and say here target arrows and target directions, save, refresh. And now you see these darker arrows next to the others showing a kind of offset that we need to measure and account for, like how much we need to rotate these detected directions to match the target ones. And for that, I'm going to cheat. We need a 3D rotation function that works with all the angles, and I'm going to use Three.js to implement it. For now, at least. So given XYZ and some angles here, we are going to make use of the vector class in Three.js. And the rotation, we can use this Euler class and call apply Euler on the vector with this rotation and just return the vector. Now to test if what we did here is correct, because maybe we made some mistake passing parameters, we can try going to main.js, where we have this tip position calculated using that sloppy math from earlier. So now we have a different function for rotating things. We can consider the pen as a vector centered at the camera position and rotate it according to those angles with the new function we just created. So instead of this, we can remove it and get first the pen vertical vector from the camera's point of view, so minus the pen height. And now the rotation, we just rotate this pen vertical using this angle information. And to get the tip, we add 3D to the camera position, this pen rotation. So we need to implement this add 3D as well. And that's going to be same as this subtract 3D, but calling it add 3D and with a plus. So if this works, this should still look like a circle pretty much. And it does. It means that we are accounting for the rotation correctly with the new function as well. Now we're given some directions, have some target ones, and need to find the rotation, the pitch, yaw, and roll angles that make them align. I tried to solve this analytically, but failed. Even going beyond high school level didn't help me out. But it's okay, because we can also consider this as an optimization problem. I'll show you how to apply local search here too, so you understand how useful the technique really is. Pause the video now to think how we might do that. The code will be pretty much the same as before, with one key difference. That difference is the evaluation function. Previously, we measured how good or bad the position was. Now we need to measure how good or bad the rotation is at aligning the given directions with the target ones. We can choose to implement this as an error function like earlier, or a scoring function. For the sake of completeness, let's see how to climb the hill and implement a scoring function this time. We need a function for measuring the score, the rotation score. Given some angles, like a pitch, yaw, and a roll, how good are these angles at modifying the directions to become the target directions? We'll have to process each direction one by one, so we compute a total score starting at 0, and now looping through all of them, we first get a rotated direction. So what happens to this direction here if we rotate it given the angles in the parameter up here? And now we can calculate the alignment between this one and the corresponding target direction and add it to the total score. For this, we can use the dot product. We're going to need a 3D implementation of it. So we pass the rotated direction and the target direction vectors. And finally, we return this total score. The dot product goes in the vector.js file, and it's a simple function that takes two vectors as a parameter and returns a value between -1 and 1. By multiplying the coordinates in this way, we get a value that is close to 1 if the vectors are aligned and close to 0 if they are orthogonal. Actually, it gives also negative values, so -1 would be if the vectors are pointing in opposite directions. Considering this is a score, it's going to get higher and higher if the value returned by this is higher. Maybe sometimes the score goes down from the negative values, but overall we are expecting a value of 3 here if they're perfectly aligned. So we can use this now to search for a maximum score instead of a minimum error. And we can start our search with any given rotation, let's say 0, 0, 0. And the max score, I'm setting it to -infinity this time. The number of iterations, let's set them to 10,000 as before. And the max step, I'm going to use the same randomized approach as previously. It's going to be a little smaller this time because we're working with angles in radians. So we don't want to make as large steps as previously. Like here, a value of 3 something is all the way back. We want smaller jumps. And we iterate how many iterations we have. And now we can calculate our candidate. We just define the pitch to be the rotation pitch, plus a random value in the interval minus max step plus max step. The same thing goes for the yaw and the roll. So the yaw and the roll. The yaw and the roll. And we can score this candidate. So using the rotation score function from previously, if we found a score that is better than the max score, it becomes the max score. And we found a better candidate. That's it. If everything works, we should be able to replace here this rotation that we found with the one coming from the metadata, and we don't need to do anything anymore. Almost. Save. Refresh. And it looks okay. I mean, remember what we had previously. If this rotation would be just 0, like if we never update it from this original value, it's all over the place. It seems to work. Let's visualize also those direction vectors. Like, how would they look like if they are gonna be rotated by this rotation that we found? And they're going to be updated already here when we view them on the canvas. Save, refresh, and they do look aligned with the other vectors. Because we finished working with the metadata from the simulator, we can test this version now with the real video as well. Let's choose the first one. Looks pretty good, I think, but it's kind of small. Let's make it bigger. I'm going to go in the output here and let's return these to a larger scale and offset it also as it was. I think it was times 0.1. Okay, looks a bit noisy, but many of those homework ideas I gave you will help reduce this noise. So I'm gonna let you explore that. And now we could test this to see how well it does in the competition. Like on the competition page, there is the test page. So the first drawing, we could calculate the coordinates and drag it there. But before that, we still need to properly implement a 3D rotation function, not using Three.js. I feel I need to emphasize why it's important we do this, because I often get students asking me, why when it's so easy like this? Or why waste more time on this? It works already, or we're already using Three.js, no reason to stop using it now. And honestly, I get it. It's tempting to stick with what works and move on to something else. But the fact of the matter is, we never relied on Three.js until now. We only used it to visualize and understand things. Up until now, we could have removed it entirely and the solution would still work. It's the math that's important. All those visualizations can go away even. That independence was a strength. But now we start depending on Three.js, and that can be a bad thing. Like, now it comes over the internet, so we depend on a network connection. Sure, you could add it to the project locally, but now your software is much bigger. The complexity increased by a lot. And Three.js can do all this fancy 3D stuff, but we're only using one calculation. Now, one library is not such a big problem, but beginners learn they can solve different problems using different libraries. And when the software grows, it tends to become a giant mess. This is a big problem I've seen in many code bases. To rotate things in 3D, people use matrices a lot. But I'm going to show you a way to do it here that is more in line with the code we have already, relying on multiple 2D rotations. So this is going to be a 2D rotation function given a vector and an angle. We just take its direction and calculate the new direction after adding that angle. And then we're going to create a new vector with that and the original vector's magnitude. So we can return here magnitude times the cosine of the new direction, magnitude times the sine of the new direction. And with this function, we can create a 3D rotation function. So this one has an x, y, z here for the position and a pitch, yaw, roll for the angle components. And for this function to be as clear as possible, because we're going to call this other function to rotate on different planes, it helps if we take out here the x and the y and write it a little differently. So this would be x and y passed separately, but here we do need the vector because our direction and magnitude work with this compound object. So I'm going to create it here like so and copy it for the magnitude as well. And when we return, it also helps if we consider this as an array so that we don't have to type x and y when the rotation has been done in a different plane than x and y. I hope you're going to understand why I do this, but anyway, I do this, otherwise more confusion comes afterwards. So here it's going to look like that. And now, first thing we do is rotate in this plane using the pitch and update the y and z values. X stays the same. Then on this other plane we use the yaw to update x and z. Y stays the same. And this is the final step. Using the roll on this final plane, we update the x and y, and z stays unchanged. When all these combine, my job is done. Save, refresh, choose the first video, and it should be pretty much the same we had earlier. Your 11th homework is to self-study rotation matrices and re-implement the rotate 3D function to use them instead. Now, to get the coordinates from here, we can use the console, and I'm just going to start with an empty string like this, and then do a quick for of, going through all the positions, like so, and adding a new line at the end. We can make a file out of this and drag it here to get this result, compared to the red showing what the results should be like. Now, this puzzled many during the competition, and for good reason. It's hard to figure out, especially if you don't have that list from earlier. To understand what's going on, we'll need a different perspective. We'll update the output to display a side view as well. I got this idea from James, and I think it's much clearer than switching to a 3D output, and quicker to implement. Let's go in the output here and update it to visualize a side view as well. So I'm going to split it vertically, most of it is going to stay the same, and then on the right we're going to have a narrow part for the side view of the table. Let's go here after we clear everything and define the top view width. I'm going to say this is 80% of the original one, and the side view is going to be what's remaining, so 20%. Now, this top view width is going to be where we translate here. So it's going to be the center of the top view canvas. And let's draw a line here, separating the two, a vertical line. So going to the top view width 0 and to the top view width height and stroke. Save, refresh. I'm just going to use the simulation. It appears here. Now let's make it a little thicker and draw a line in the middle as well that will kind of represent the table. So maybe line width set to 2 and copy this. I want this one to be thinner, maybe 1 here. And let's add to this one half the side view width as well. Yeah, something like that. Now let's label this part also. We have the top view here. Let's put the side view there. I'm going to copy this below and use some transformations to help. So I'm going to save and then translate to the right and rotate by 90 degrees or half pi. And after I'm done with this, I'm going to restore and name this side view. Refresh and it's okay. We don't really need to set this again and this again and this again. So I think this should work as well. And it does. And now we have to draw all these black points here as well, but with their y value instead of the z value, so that we see how high up it's from the table. To keep things simple, I'm going to go here and first translate by half the top view width and half the side view width, and also need to divide by this 30 here. Okay, let's quickly define a variable for it, because otherwise we will mess things up later. And actually, this is just the width. Sometimes simplifying like that is more clever. And after we translate it there, we can copy this, but use a y here instead. And actually for the simulation, we can even copy this if we want to draw the real one in red. So using the y here and here, save, refresh. And you can see in the simulation that they do appear to be on the table there, minus some noise at some point, and the red one showing the correct position. But if we load the video, this is what happens. We don't have the red indicator there because it's unknown. But you see, it tilts. This is what James noticed during the competition. And it's a little strange. I had to think, what's going on? Is it really my problem? Like, was the table not aligned? I made sure it's aligned, it's flat. This looks noticeable even without measuring it. But then could it be that one of the balls was not as close to the wall as the others, and maybe that made it look like the table is aligned? I think I measured things quite carefully. So what must be is those pixel intensities from the beginning. Like the red, green, and blue didn't have the same kind of intensity there. And that can have an effect on the side pixels if they're taken into account as well. If we log these RGB counts again, now after we accounted for the distortion, you'll see already in the beginning the red has more than the green. This is the lowest, and then the blue is somewhere in the middle. So I think this accounts for this tilt, and also the other tilt, this kind of oval shape that goes in this direction that EOS noticed. Let's remove this, and let me show you what happens in image processing if we define a different threshold for red. We just take it and use it here instead. It looks better, right? But this oval tilt is still not fixed here. So we actually need another threshold for that, different than this 80 that we used to have. It appeared smaller than the others, so this one is going to fix it here. When we do that, the green has an impact on that Y value as well. So actually it turns out that the threshold for the red should be more like 100. I'm going to remove this one from here and just write at the top the threshold for blue, the previous 80. And now we get something that looks like this. And it's important to point out that this kind of optimization I'm doing now tries to get this thing here flat. So I have an objective. I have a score or an error that I want to minimize, maximize, whatever. You can use local search for this. So you can automate this process. And because I'm quite confident that the setup was level, I think it's okay to do this. And now if we do the same thing again from previously, it's much better. There's still some noticeable oval shape here, and that one comes from the FOV. If I go to the parameters here, previously we had just a guess here. If we replace with 58, it's gonna give a better result. And again, in the same way, you can use that roundness measure to make this oval look less of an oval and optimize that parameter as well. I hope you realized these examples of how to use local search or some other optimization technique and how important these are and how generally useful they are for different things. Now let's get the coordinates. There it is. What's left is to try other videos as well. Now for the others where the pen gets lifted off the table, I'm gonna need to go to main.js at the top and change this into a let. Save, refresh, choose the third video. And now that part where the pen gets lifted up. So that you can see it here in this side view quite clearly. We need to ignore those points. And now to filter out the points that are off the table, I'm going to get the tip positions as a backup here, and then update them by filtering the backup to keep those with y less than 2. And you see many of them disappeared. Maybe we can go even less, so something like 1. I think this is fine. And with the previous code snippet here, we can take the coordinates and drag it here. All right. I won't reveal the rest of these numbers because I don't plan on taking first place. I'm going to leave that up to you. So let's keep the competition going. If you followed along and did the homework assignments, you can get some really good looking results. But there's still room for improvement. Like here, I'm sure these are happening because the camera shakes. AOSAS did some experiments to remove that kind of blur, but no one found a way to really fix it. There were other clever ideas during the competition too, like using the audio to detect when drawing happens. Listen to the video and you'll notice the pen makes a noise when moving on the table. I think it's a great idea to try out because when drawing, it's enough to lift the pen just a little bit. So using the Y value threshold alone might make it hard to tell those apart. I did exaggerate those movements when recording the videos, but still. You can check others' code for examples. Yusuf has one in JavaScript in case you want to integrate it into this version. One great thing about most of the others' methods is we can reproduce those results. The method I taught you here doesn't give the same result each time, partially because of the randomness from local search, but more importantly because of how we process the video. Playing it in real time means it skips some frames here and there. I wanted to do this because of what Yusuf said in the beginning. He decided to make it work live, like we could now connect it to a webcam instead of a video and decode the drawings in real time. But others made sure they process every frame of the video, and that's the only way to know for sure if an update improves the results or not. Otherwise, the accuracy will jump all over the place. In that way, you also get more samples and can consider new ideas, like smoothing as a post-processing step. If you want to learn how to process the video frame by frame, you can have a look at James's code. It shows how to do it in JavaScript. And one more thing, you see how these directions always appear on the inside of the target ones? It's because we don't calculate them correctly at the moment. We are using this projection, so the true direction gets refracted somehow. But even if we switch to use the original, now we just average, so we get the middle here instead of this other point that would be where the center of the ball is if we'd have X-ray vision or something. Your 12th homework is to implement a way to find those true centers. Some did that during the competition. Have a look at their code if you need to. The lucky thing about local search is that even with these wrong directions, it converges to something where the general alignment is okay. Because it considers all the balls equally, I think this is actually better than all other approaches I've seen in the competition. The others just used 2 of the balls or calculated the pitch and roll independently somehow. I got the feeling something's not quite right. Now, in this way, we won't find an answer with a perfect score, a total dot product of 3. But the thing is, it wouldn't find it even if the directions are calculated properly, because in the real world, my setup just cannot be 100% perfect, and the camera sensor has its limitations too. It's unlikely for that sum to ever be 3, even using the simulation. So we can't find the perfect solution here, and it's the reason solving this analytically gave me so much trouble. It's impossible to find any values that can be plugged in there to give 3 as a result. But with local search or other optimization techniques, we find something that is close to 3, and that is close to where the theoretical solution would be in an ideal world. So I'm happy with this.
What I'm not happy with is the code in main.js. Your 13th and final homework is to refactor it using descriptive function names and by merging these 2 local search implementations into a single one. Hint, you can pass functions as parameters in JavaScript.
Lastly, about neural networks. I don't think they're worth it here. Typically, neural networks work with low-resolution images as an input. Otherwise, the network size gets out of control. But if you do that, you lose the information you need to decode accurately, I think. You'd probably get something that looks like Dmitro's first solution when his coordinates didn't have enough precision. I might be wrong if the network can learn to do super resolution somehow, but my hunch is it won't be able to. Alternatively, you can feed the network tailored features, like the size of the balls, their centers, the parameters from here. I think should also tell it something about the distortion, or pass more parameters like the size of the screen so it can figure it out. Anyway, if we know to give it all that, we probably know how to solve the problem ourselves already. So what's the point? About training the network, Boss's approach was to use the simulation to generate data for it. And I think it's a good idea. Maybe it could even learn to adapt to different camera parameters if trained on simulations with different settings. You could also consider neuroevolution, like in the self-driving car course. You can use that roundness measure as a fitness function, instead of how far the car was driving without an accident. Training would be slower, but with the small network, I think you could get some results. Let me know if you try any of these AI things, especially if you get better results than Boss did during the competition. And that's about it. Hope you liked the course. I think I packed it with a lot of useful things. So many that I'm probably gonna stop posting videos soon. I feel I have nothing left to teach at the moment and want to do other things. For a while at least. Thanks for watching and see you guys.
Maybe I can win next time.